Welcome to this tranquil journey through time and space. We begin our exploration at the very dawn of existence, when the universe was but an infinite void, silent and serene. Close your eyes and imagine the vast emptiness where nothingness reigns supreme. In this boundless void, approximately 13.8 billion years ago, something extraordinary began to unfold. Behold the moment of the Big Bang, a powerful explosion that was not just an event, but the very inception of space and time itself. It marked the beginning of everything we know, the beginning of the universe. In this monumental event, the universe was born from a singularity, an infinitely dense point that contained all the matter and energy of the future cosmos. For a brief moment, as the universe expanded, temperatures soared to unimaginable levels, reaching trillions of degrees. In this primordial stage, quarks and gluons, tiny fundamental particles, danced wildly, creating a hot swirling soup known as quark-gluon plasma. As the universe continued to expand and cool, about a fraction of a second after the Big Bang, these quarks began to combine, forming protons and neutrons. This marked the first step toward creating the atoms that would eventually make up the stars and planets. Barely 3 minutes into its existence, the universe had cooled enough for these protons and neutrons to undergo a process called nucleosynthesis. During this time, they fused together to form the lightest elements: hydrogen, helium, and trace amounts of lithium. These simple elements would serve as the building blocks for more complex structures to come. As we reach the first few 100,000 years after the Big Bang, the universe was still a hot, glowing place, filled with the light of newly formed particles and radiation. This era is known as the cosmic microwave background, a faint afterglow that still permeates the universe today, a remnant echo of that momentous inception. Slowly, as the universe expanded further, it cooled enough for electrons to join with protons, forming neutral hydrogen atoms. This monumental transformation allowed light to travel freely for the first time, illuminating a vast, dark expanse. This period is called Recombination, and it paved the way for the creation of the first galaxies. With the formation of galaxies, clusters began to coalesce. These magnificent structures, consisting of stars, gas, and dark matter, began to emerge. Under the force of gravity, the universe's tapestry began to thicken as clumps of matter drew together, forming the cosmic web. As the stars ignited, they burned brightly in a cosmic ballet, crafting heavier elements within their fiery cores through the process of fusion. Some would culminate their lives in brilliant supernova explosions, scattering these precious elements across the universe, key ingredients for life as we know it. As we gently drift through the fabric of the cosmos, we can reflect on these moments, the birth of galaxies and stars, and the timeless dance of creation. Each soft glow in the night sky carries the history of our universe, a reminder of our shared origin. Now, let's continue our voyage into the mysteries of deep space and the wonders that lie ahead. Continuing our journey through the grand narrative of the universe, we delve deeper into the realms where light meets darkness, where stars ignite and galaxies flourish. As we traverse through time, let us pause to admire the cosmic dawn. Approximately 1 billion years after the Big Bang, the first stars began to twinkle into existence. These ancient beacons of light were unlike any we know today. Massive, bright, and short-lived, their intense heat catalyzed the formation of more complex elements, forging the foundations for future solar systems. These early stars ushered in the era of reionization, a time when the universe, once opaque, became transparent as the radiation from these stellar giants ionized the surrounding gas. For the first time, the cosmos was bathed in a warm and radiant glow as the darkness receded before the brightness of countless new stars. As we drift forward in time to around 2 to 3 billion years after the Big Bang, the universe was alive with activity. Gas clouds, rich with hydrogen and helium, began collapsing under their own gravity, forming dense regions that sparked stellar births. Within these swirling clouds, entire star clusters formed, nurturing the cosmos' diversity. With the birth of these stars came the emergence of galaxies, vast and magnificent structures that would soon weave themselves into the fabric of the universe. Our own galaxy, the Milky Way, formed during this time, condensing from primordial gases and stars around it. It became a haven for countless stars, planets, and other celestial wonders, a place where new worlds would eventually rise. The universe continued to expand, and the gravity of matter created gravitational wells that drew in more material, accelerating the birth of more galaxies. Around 5 billion years after the Big Bang, galaxies began to collide and merge, a cosmic tango that shaped their evolution. These dramatic encounters sparked waves of star formation, igniting new stars as dust and gas were thrown together in stunning celestial fireworks. As we reach the midpoint of our journey, about 6 billion years after the Big Bang, we witness the dynamic interplay of forces within the cosmos. Dark matter, an invisible yet crucial component of our universe, played its role as a glue binding galaxies and galaxy clusters together. Although we cannot directly observe it, we can feel its presence through the gravitational effects it has on visible matter. Meanwhile, life across the universe began to emerge in those regions where matter coalesced into rocky planets and rings of dust. Amidst the swirling arms of galaxies, planets formed in a process as ancient as the stars themselves. Here, the dance of creation continued, setting the stage for life in its many forms. Eventually, around 9 billion years after the Big Bang, the cosmos tuned to a slow, expansive rhythm. Larger structures began to emerge, superclusters of galaxies, interconnected in vast networks, weaving a cosmic tapestry. The universe's accelerating expansion, driven by mysterious dark energy, became a dominant force, pushing galaxies further apart over time. Our universe's unfolding story is not merely a tale of chaos and accidents, but rather a symphony of harmony and intricate design, a reminder of the delicate balance that governs nature. Each moment, from the fiery birth of a star to the tranquil drift of galaxies, is steeped in cosmic significance. As we drift through this saga of creation, we find comfort in the understanding that we are all part of this wondrous universe. The stars that twinkle in the night sky are the echoes of our own beginnings, whispering secrets of creation and existence. Let us continue to embrace the mysteries that unfold as we journey closer to our present-day cosmos. Our voyage continues, a gentle exploration of the universe as it further evolves. As we move into the next chapter of cosmic history, let us marvel at the formation of our local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and several smaller companions. These celestial neighbors began to take shape around 10 billion years after the Big Bang. Their delicate dance and gravitational interactions laid the groundwork for the vast structures we observe today. Rising through this celestial landscape, we arrive at a key moment around 11 billion years after the Big Bang. The universe was approximately 1/4 of its current age, yet it had already witnessed the birth and death of countless stars. Some of these stars ended their lives in spectacular supernova explosions, dispersing heavy elements into the cosmos. Elements like carbon, oxygen, and iron, vital components for creating planets and life, became part of the interstellar medium, enriching the universe's chemical diversity. As we journey forward to around 12 billion years after the Big Bang, we encounter the phenomenon known as galaxy cannibalism. Larger galaxies began to gravitationally feast on their smaller companions, merging into larger structures. This process altered their shapes and sizes, transforming them into the majestic spiral and elliptical galaxies we observe in the night sky today. In this vast ballet of cosmic creation, let us focus on our own Milky Way. It formed around 13.6 billion years ago and has approximately 100 billion stars. Yet, it is but one of billions of galaxies in our universe. As we look towards the cosmic horizon, we realize that the universe is a tapestry where billions of galaxies create a beautiful mosaic of starlight across the night. Now we reach a fascinating juncture: dark energy. Discovered in the late 20th century, this enigmatic force drives the accelerating expansion of the universe, making up about 68% of its total energy content. The realization that the fabric of space itself is stretching, pushing galaxies apart, challenges our fundamental understanding of physics and the very nature of reality. As we travel further through cosmic time, we discover that the universe's expansion allows for the creation of new structures. Around 13 billion years after the Big Bang, the first quasars emerged, supermassive black holes at the centers of forming galaxies, shining brighter than entire galaxies themselves. These quasars serve as beacons of light in the universe, shining brightly across vast distances and helping us peer back in time to moments when galaxies were in their infancy. Around 13.7 billion years ago, we come upon an extraordinary moment, the formation of our own solar system. Out of the remnants of ancient stars scattered across the galaxy, gas and dust coalesced into a swirling disk. Through this intricate process, our sun ignited, marking the beginning of a new chapter in the universe's story. In this very disk, planets began to form, setting the foundation for our own Earth, a sanctuary in the vastness of space. As we conclude this serene passage through the cosmos, we are reminded that the universe is an ever-evolving masterpiece, full of intrigue, energy, and a sense of calm, yet infinite possibility. The interconnections forged between galaxies, stars, and planets illustrate a grand design, one that echoes through the ages and resonates within each of us. With this understanding, we gently reflect on our own place within this magnificent expanse, knowing that we are part of the universe's eternal dance. Let us take a deep breath and bask in the beauty of existence as we continue our gentle journey through time and the cosmos, revealing more wonders of our universe in the segments to come. As we delve deeper into the universe's majestic evolution, we approach a time where the stages of formation and creation intertwine seamlessly. Each moment is a reminder of the intricate tapestry woven throughout the cosmos. Let us journey back around 4.5 billion years ago as we focus our attention on our own solar system. Out of the protoplanetary disk surrounding the young sun, the Earth began to take shape. A collection of dust and gas coalesced, heating up due to gravitational forces, a process known as accretion. Eventually, Earth became the third planet, nestled in the perfect distance from the Sun, known as the habitable zone. Here, conditions were just right for the emergence of life. Not long after Earth's formation, our moon came to be, a beautiful celestial companion. In a cataclysmic event, a Mars-sized body named Theia collided with the early Earth. The debris from this collision eventually coalesced to form Moon, stabilizing Earth's axial tilt and creating tides that would prove crucial for the development of life. As we continue forward in time to around 3.5 billion years ago, we begin to witness the first signs of life on Earth. Simple, single-celled organisms known as prokaryotes surfaced in the primordial oceans. These tiny life forms thrived in a world without oxygen, relying on chemosynthesis and photosynthesis to survive. They would lay the groundwork for all complex life forms to follow. Fast forward to about 2 billion years ago, a monumental shift occurred. Photosynthetic organisms released oxygen into the atmosphere, leading to what is known as the Great Oxidation Event. This influx of oxygen transformed Earth's atmosphere and oceans, enabling the rise of aerobic life forms, significantly impacting the evolutionary pathway of all subsequent species. As we reach approximately 600 million years ago, we begin to see multicellular life evolve, paving the way for complex ecosystems. The Cambrian explosion, occurring around 541 million years ago, heralded an incredible diversification of life forms as creatures began to inhabit the various water environments. This period marks the rise of complex body plans and the emergence of ancestors to many modern groups of animals. Evolving continuously, around 250 million years ago, the Earth experienced the Permian-Triassic extinction event, the most significant mass extinction recorded in Earth's history. An estimated 90% of all species perished during this time, reshaping the landscape of life and paving the way for new species to rise and evolve. Now, as we approach a crucial era, approximately 65 million years ago, the Earth bore witness to another major extinction event. The impact of a gigantic asteroid near the Yucatan Peninsula changed the course of evolution, bringing about the end of the dinosaurs and allowing mammals to flourish and diversify in the subsequent age of the Cenozoic. As we stand on the beautiful planet Earth, we reflect on a chain of events that not only shaped our world, but also brought forth the essence of life. From cosmic explosions to the delicate balance of ecosystems, each moment is interconnected, revealing the narrative of our origins and the universe itself. As we float back through the cosmos, we are reminded that our own existence is a product of this magnificent dance, a blend of chaos and order that unfolded in the vastness of space. Now, breathing deeply, let us embrace the wonders yet to come as we prepare to explore further into the heart of the universe's history, unfurling the mysteries that envelop us in this vast cosmic journey. As our cosmic narrative unfolds, we find ourselves at a pivotal moment in Earth's history, one where life flourished and evolved in marvelous ways, illuminating the interconnectedness of all existence. Let us drift back to around 2 million years ago, when the first Homo sapiens emerged in Africa. This species, with its remarkable brain capacity and ability to adapt, began to develop tools, language, and social structures. Their evolution marked a significant step in the story of life on Earth, paving the way for the intricate cultures and societies that would arise later. Moving forward around 10,000 years ago, humans transitioned from a nomadic lifestyle of hunting and gathering to settled agriculture, a pivotal moment known as the agricultural revolution. By cultivating crops and domesticating animals, we established permanent settlements, leading to the growth of villages and, eventually, the birth of civilizations. This transformation allowed communities to thrive and flourish, shaping the identity of humanity. As we journey through the past few thousand years, we witness the rise of empires and advancements in technology, arts, and sciences. The invention of writing, around 3200 BC, in ancient Mesopotamia allowed civilizations to record their histories, share knowledge, and communicate ideas across generations. It set the foundation for the learning and progress that would characterize human advancement. Jumping forward to the 16th century, we enter the Age of Exploration, a time when humans began to look beyond the horizons of their own lands. Discoverers set sail across oceans, connecting continents and exchanging cultures, knowledge, and ideas. This era ignited a thirst for understanding the world and its mysteries, ultimately leading to the scientific revolution. As we take a deep breath and settle into the 20th century, we come face to face with a remarkable achievement, the advent of space exploration. In 1969, humanity made history as astronauts aboard Apollo 11 landed on the Moon. This monumental event was not just a technological triumph, but a testament to human curiosity and the desire to explore the cosmos. It served as a reminder of our connection to the universe, and the Moon, a silent witness to our journey through time. With our eyes turned skyward, we enter the realm of the cosmos, the discovery of exoplanets. Since the late 20th century, astronomers have identified thousands of planets outside our solar system. This astonishing revelation raises profound questions about the potential for life on other worlds. Each exoplanet discovered enriches our understanding of the universe and humanity's place within it. As we venture deeper, we witness the emergence of advanced telescopes and technology that allow us to peer back in time. The Hubble Space Telescope and its successors have unveiled breathtaking images of distant galaxies, nebulae, and celestial phenomena. These insights reveal not just the beauty of the universe, but its history and the processes that govern it, opening our minds to the vast possibilities that lie beyond. At last, as we reflect on our journey through both the micro and macrocosm of existence, we recognize that Earth is a tiny blue dot in the vast expanse of the universe. We are part of an intricate web of life woven into the fabric of cosmological history. Every moment, every atom in our bodies tells the story of this grand narrative, a connection that transcends time and space. As we gently return to our present moment, we embrace the idea that we are explorers, not just of our planet, but of the cosmos itself. The wonders of the universe continue to inspire and beckon us to seek knowledge, fostering curiosity and compassion, a reminder of the shared journey we all undertake. Let us take a moment to breathe deeply and reflect on our cosmic journey thus far. With each turn of the page, we uncover more of this extraordinary story, ready to explore the depths of our universe in the segments yet to come. As we breathe deeply and float gently through the currents of time, our journey carries us into some of the most extraordinary chapters of our universe's unfolding story, moments that shaped not just the cosmos, but the very conditions that allowed us to be here, contemplating it all. Let us begin with one of the universe's most powerful phenomena, gravitational waves. First predicted by Albert Einstein in 1916 as part of his general theory of relativity, these invisible ripples in the fabric of spacetime were not detected until September 14, 2015. On that remarkable day, the LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, felt the faintest tremble, a distortion thousands of times smaller than the width of a proton. That trembling was the echo of two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging in a cataclysmic collision over 1 billion light-years away. In that single moment, more energy was released than all the stars in the observable universe combined to emit in an entire second. And yet, the wave that arrived at Earth was so gentle, so impossibly subtle, that detecting it required one of the most precise instruments ever built by human hands. Gravitational waves open an entirely new window onto the universe, one that does not rely on light at all, but on the very trembling of space itself. Now let us turn our gaze to the concept of neutron stars, celestial objects of breathtaking density. When a massive star exhausts its nuclear fuel, it collapses under its own gravity in a violent supernova explosion, leaving behind a core so compact that a single teaspoon of its material would weigh approximately 10 million tons here on Earth. These neutron stars are only about 20 kilometers across, smaller than many of our cities, yet they contain more mass than our entire Sunday. Some neutron stars spin hundreds of times per second, emitting pulses of electromagnetic radiation with the regularity of a cosmic clock. We call these pulsars, and astronomers have used their extraordinary precision to study everything from gravitational waves to the behavior of matter under extreme conditions. The neutron star is nature's way of showing us just how much mass the universe can compress into the smallest of spaces. As we drift deeper, we arrive at perhaps the most mysterious residence of our cosmos, black holes. Born from the deaths of the most massive stars, black holes are regions of spacetime where gravity is so intense that not even light can escape. They are, in a sense, the universe's best-kept secrets, for we cannot observe them directly. And yet we know they exist. We see stars orbiting invisible points at the centers of galaxies at dizzying speeds. We watch matter heat up to millions of degrees as it spirals inward, forming luminous accretion disks. In April 2019, humanity achieved something once thought impossible: the first ever image of a black hole silhouette captured by the Event Horizon Telescope. At the center of the galaxy Messier 87, some 55 million light-years away, we glimpsed a dark void ringed by fire, a shadow cast by a black hole 6.5 billion times the mass of our Sun. It was a moment of profound wonder, a reminder that the universe still holds secrets we are only just beginning to uncover. Let us now reflect on something that surrounds us yet remains completely invisible: dark matter. Though it cannot be seen, touched, or directly measured, dark matter accounts for approximately 27% of the universe's total mass and energy. We infer its existence from the way galaxies rotate. Their outer edges spin far too quickly to be explained by the visible matter alone. Something invisible must be providing additional gravitational pull, holding galaxies together like a vast cosmic scaffolding. Without dark matter, the galaxies we know and love, including our own Milky Way, would fling apart, unable to maintain their majestic spiral forms. Dark matter is one of the greatest unsolved mysteries in all of physics, a reminder that the universe we can see with our eyes and instruments is merely a small fraction of everything that actually exists. Equally mysterious is dark energy, and here the universe presents us with its most startling surprise. In 1998, two independent teams of astronomers studying distant supernovae made a discovery so shocking it would earn its lead researchers the Nobel Prize. The expansion of the universe is not slowing down. As gravity would suggest, it is accelerating. Something is pushing the fabric of space apart, faster and faster with every passing moment. We call this force dark energy, and it constitutes approximately 68% of the total energy content of the universe. We do not know what it is. We cannot see it, capture it, or replicate it in a laboratory. Yet it governs the ultimate fate of everything. If dark energy continues its work unchecked, galaxies will one day drift so far apart that even the night sky will go dark, a cold, silent, isolated cosmos stretching out into an endless void. From the largest scales of the universe, let us travel inward to something closer to home: the remarkable story of water. Water, that humble molecule of two hydrogen atoms bonded to one oxygen, is believed to be among the most common molecules in the universe. It exists in the clouds of interstellar gas, on the surfaces of comets, and hidden beneath the icy crusts of moons like Europa and Enceladus. On Earth, water covers approximately 71% of the surface. It was likely delivered to our young planet by comets and asteroids billions of years ago, and it became the very medium in which life first sparked into existence. The chemistry of life as we know it is, at its heart, the chemistry of water. Every living cell on Earth is composed largely of it. And as we search the cosmos for other worlds that might harbor life, water remains our most important guide, our most precious sign that life might be possible elsewhere in the stars. As we move through this cosmic narrative, let us pause to contemplate the speed of light itself, one of nature's most fundamental constants. Light travels at approximately 299,792 kilometers per second, so fast that it could circle the entire Earth more than 7 times in a single second. And yet, even at this incomprehensible speed, light takes time to reach us. The light from our sun takes about 8 minutes and 20 seconds to arrive. The light from the nearest star beyond our sun, Proxima Centauri, takes over 4 years. And the light from the most distant galaxies we can observe has been traveling for over 13 billion years. This means that when we look up at the night sky, we are not seeing the universe as it is, we are seeing it as it was, a cosmic time machine written in light. The further we look, the deeper into the past we see, all the way back to the earliest moments of the universe itself. Now let us consider the extraordinary idea that we ourselves are made of stardust. Every atom of calcium in our bones, every atom of iron in our blood, every atom of oxygen we breathe was forged in the heart of a dying star. The hydrogen in our bodies dates back to the Big Bang itself. When massive stars reached the end of their lives and exploded as supernovae, they scattered these atoms across the cosmos, seeding future solar systems with the raw materials of chemistry and, ultimately, of life. The astronomer Carl Sagan perhaps said it best, "We are a way for the cosmos to know itself." The atoms that make up every human being on Earth have spent billions of years traveling through space, through stellar nurseries, through the protoplanetary disk of our early solar system. We are not separate from the universe. We are a part of it, a beautiful and fleeting expression of its endless creativity. And so we arrive at a profound question that has captivated humanity across all cultures and all ages. Are we alone? The search for extraterrestrial life is no longer merely the domain of science fiction. The discovery of thousands of exoplanets, planets orbiting other stars, has revealed that planetary systems are common throughout the galaxy. Some of these worlds orbit within the habitable zones of their stars, where liquid water could exist on their surfaces. Missions like NASA's James Webb Space Telescope are now analyzing the atmospheres of distant worlds, searching for the chemical signatures of life. Closer to home, the moons of Jupiter and Saturn harbor vast subsurface oceans beneath their icy surfaces where the conditions for life may have been sustained for billions of years. Whether life exists elsewhere remains one of science's greatest open questions, but the odds, in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, seem increasingly favorable. As we gently return from the farthest reaches of the cosmos, we carry with us a deeper sense of connection to the stars, to the atoms within us, to the vast and beautiful story that began 13.8 billion years ago and continues still. We are not passive observers of this universe. We are its participants, its storytellers, its most curious creation. Let us breathe deeply, rest in that awareness, and prepare to journey onward into the wonders still waiting to be discovered. We breathe deeply and we continue. Our journey through the cosmos has brought us face to face with black holes and gravitational waves, with stardust and the search for life. Now, as we drift onward through the quieter corridors of space and time, let us explore some of the universe's most profound and humbling secrets, stories written in light, in silence, and in the invisible architecture of existence itself. Let us begin with the largest structures in the known universe, cosmic filaments. When we zoom far enough out, beyond individual galaxies, beyond galaxy clusters, beyond even superclusters, we encounter something almost incomprehensible in its scale. The universe is not scattered randomly. Instead, it is organized into a vast cosmic web, a network of enormous filaments, stretching hundreds of millions of light-years, connecting clusters of galaxies like threads in a colossal spider's web. Between these filaments lie immense cosmic voids, near-empty regions of space, so vast that entire galaxy clusters appear as mere specks along their edges. The largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, spans approximately 10 billion light-years across. To put that into perspective, the entire observable universe is only about 93 billion light-years wide. We are looking at a single structure that stretches across roughly 1/10 of everything we can see. In these great filaments and voids, we glimpse the universe's truest face, not chaotic, but elegantly, breathtakingly organized. As we float gently through this cosmic web, let us turn our attention to one of the most extreme environments in the known universe, a magnetar. A magnetar is a special type of neutron star, and it possesses the most powerful magnetic field of any known object in existence. Its magnetic field is so intense, roughly a quadrillion times stronger than Earth's own magnetic field, that if a magnetar were to drift as close as halfway between Earth and the Moon, its magnetic force would erase every credit card on our planet, disrupt the iron in our very blood cells, and prove lethal to any living thing in its vicinity. Magnetars occasionally release enormous bursts of energy known as starquakes when the immense stress of their magnetic fields causes their crusts to fracture, events so powerful they can be detected from across the galaxy. In December 2004, a magnetar known as SGR 1806-20 released a burst of energy in just 0.2 of a second that exceeded the total energy output of our Sun over 250,000 years. It was the most energetic event ever observed from beyond our solar system. The universe, it seems, still has ways of humbling us. Now we breathe and turn toward something closer, our own atmosphere. The thin shell of air wrapped around our planet is a marvel of cosmic fortune. Earth's atmosphere is approximately 78% nitrogen, 21% oxygen, with trace amounts of argon, carbon dioxide, and water vapor. It shields us from the harshest ultraviolet radiation of the sun, burns up most of the meteoroids that venture too close, and distributes heat around the globe, keeping our world habitable. But what is perhaps most extraordinary is how razor-thin this protective layer truly is. If Earth were the size of a standard classroom globe, the entire atmosphere capable of sustaining life would be thinner than a single coat of varnish on its surface. We live in an extraordinarily delicate bubble, suspended between the emptiness of space and the molten interior of our world, and that bubble is the reason we are here at all. Let us travel further out and reflect on the nature of time itself. We experience time as something linear, a river flowing in one direction, from past to future. Yet physics tells us a far stranger story. Einstein's theories of relativity revealed that time is not fixed. It stretches and compresses depending on gravity and velocity, a phenomenon called time dilation. An astronaut orbiting Earth at high speed ages very slightly more slowly than someone standing on the ground, not by much, but measurably, verifiably so. Near a black hole, where gravity is almost incomprehensibly powerful, time slows so dramatically that to an outside observer, an object falling toward the event horizon would appear to freeze at its edge, suspended in time forever. On the grandest scales, time as we know it did not exist before the Big Bang. It came into being along with space, matter, and energy. Time is not the stage on which the universe performs. Time is part of the performance itself. Drifting forward, let us pause to consider one of the most beautiful events in stellar life, the formation of a planetary nebula. When a star roughly the size of our Sun reaches the end of its life, it does not explode in a supernova. Instead, it undergoes a far more graceful transformation. Its outer layers puff outward gently over thousands of years, forming a glowing cloud of ionized gas illuminated from within by the hot, exposed core, what remains of the star's heart, now called a white dwarf. These planetary nebulae come in breathtaking shapes, perfect rings, hourglass forms, delicate butterfly wings of glowing gas spreading across several light years. The Cat's Eye Nebula, the Ring Nebula, the Butterfly Nebula, each one is a dying star's final gift to the cosmos, a luminous sculpture lasting tens of thousands of years before dissolving back into the interstellar medium. Our own Sun will one day create such a nebula, approximately 5 billion years from now, painting the surrounding space in gentle veils of light before fading peacefully into a quiet white dwarf. Even endings, it seems, can be beautiful. As we breathe and settle deeper into our journey, let us reflect on the concept of entropy, the universe's quiet, patient tendency toward disorder. In physics, entropy is a measure of disorder or randomness in a system, and the second law of thermodynamics tells us that in any closed system, entropy will always increase over time. The universe itself is subject to this law. Stars burn through their fuel. Galaxies scatter. Heat dissipates. Complex structures ultimately break down into simpler ones. Given enough time, and we are speaking of timescales almost beyond imagination, the universe will reach a state of maximum entropy, sometimes called the heat death of the universe. All stars will have burned out. All black holes will have slowly evaporated through a quantum process called Hawking radiation. The cosmos will become an utterly cold, dark, and uniform expanse, with no gradients of energy left to drive any process, any event, any thought. And yet, in the vast gulf of time between now and then, entropy's very existence is what makes complexity possible. It is because things flow from order to disorder that energy moves, that stars burn, that rivers run, and that life exists. Let us turn now to one of the most mysterious and tantalizing ideas in modern cosmology, the multiverse. According to some interpretations of quantum mechanics and inflationary cosmology, our universe, vast and ancient as it is, may be just one of an unimaginably large number of universes. In the theory of eternal inflation, the rapid expansion that occurred just after the Big Bang may never have fully stopped. Instead, it continues in regions beyond our observable horizon, perpetually giving birth to new pocket universes, each potentially with its own physical laws, its own constants, its own version of space and time. Some of these universes might have different strengths of gravity. Others might have no stars at all, or matter that behaves in ways entirely foreign to us. We cannot observe these other universes. By definition, they lie beyond the reach of any light or signal that could ever reach us. But the mathematics that describes our own universe hints strongly that we may not be alone in a deeper sense than we ever imagined, not just among planets and galaxies, but among entire universes. Drawing our gaze back to Earth, let us marvel at the phenomenon of bioluminescence, nature's own quiet light in the darkness. Across our oceans, thousands of species of marine life have evolved the ability to produce their own light through chemical reactions within their bodies. From the ghostly glow of deep-sea anglerfish to the electric blue shimmer of bioluminescent plankton that lights up breaking waves on warm summer nights, life has found a way to carry starlight into the deepest corners of our world. Bioluminescence has evolved independently dozens of times across the tree of life, suggesting it is not a cosmic accident but a deeply practical tool, used to attract prey, communicate with mates, confuse predators, or simply illuminate the path forward. In the pitch-black depths of the ocean, where sunlight has never reached, life glows. It is a reminder that wherever conditions permit, life finds a way to shine. And so we arrive at our final reflection for this passage, the nature of consciousness itself. Of all the phenomena in the known universe, none is more mysterious, none more intimate, none more profound than the fact of awareness. The universe has produced over 13.8 billion years of extraordinary complexity, a being that can look back upon that universe and wonder. You sitting or lying here now, breathing gently, are the universe observing itself. The same atoms forged in stellar furnaces, the same forces that shaped galaxies, have organized themselves into nervous systems capable of curiosity, love, grief, and awe. Science can describe the architecture of the brain, the pathways of neurons, the chemistry of thought, and yet the deeper question of why there is subjective experience at all, why there is something it is like to be you, remains one of the most profound open questions in all of human knowledge. Perhaps consciousness, like dark matter or dark energy, is one of the universe's fundamental features, not an accident, but a necessary expression of the cosmos growing complex enough to know itself. As we breathe gently and allow these ideas to settle within us, we are reminded that we stand at a remarkable intersection between the ancient and the immediate, between the cosmic and the intimate. The universe that stretched itself into existence 13.8 billion years ago is the same universe humming quietly within you right now. We are not visitors here. We belong to this story as much as any star, any galaxy, any great filament of light stretching across the void. Rest in that knowing, and when you are ready, our journey continues. We return, breathing slowly, to the great unfolding. Each segment of our journey has carried us a little deeper, into the hearts of stars, into the architecture of the cosmos, into the mystery of our own awareness. Now we continue. We drift forward into new wonders, into facts that challenge, illuminate, and quietly astonish. Reminders that the universe, even after all we have learned, remains endlessly generous with its surprises. Let us begin with something ancient and invisible that surrounds Earth at this very moment, the solar wind. Our sun does not merely radiate light and warmth. It continuously exhales a stream of charged particles, mostly electrons and protons, flowing outward in all directions at speeds of roughly 400 to 800 kilometers per second. This ceaseless outpouring is called the solar wind, and it reaches every corner of our solar system, extending far beyond the orbit of Neptune into a vast bubble of influence known as the heliosphere. On Earth, We are largely shielded from this particle stream by our planet's magnetic field. But where that field dips toward the poles, the solar wind interacts with our upper atmosphere in the most spectacular way imaginable, producing the auroras. The northern and southern lights are not merely beautiful. They are the visible signature of our sun reaching across 150 million kilometers of space and gently touching our sky. Every shimmering curtain of green and violet light is a conversation between our star and our world, playing out in the ionosphere far above us. As we glide onward, let us consider a phenomenon that bends the very nature of light: gravitational lensing. When light from a distant object, such as a galaxy or quasar, passes near a massive foreground object like a galaxy cluster, the gravity of that cluster warps the fabric of space-time, bending the path of the light as it travels toward us. The result is extraordinary. We see multiple images of the same distant object, arcs of distorted light, and in the most perfect alignments, a complete ring of light surrounding the lensing object, called an Einstein ring, after the man whose equations predicted the phenomenon. Gravitational lensing has become one of astronomy's most powerful tools. It allows us to observe galaxies that would otherwise be far too faint and distant to detect. It has been used to map the distribution of dark matter. And it allows us to peer at objects so remote that their light began its journey before Earth even existed. The universe, in its elegance, uses gravity itself as a telescope. Let us breathe deeply and travel now to one of the most volatile and dynamic surfaces in our solar system, the Sun itself. The Sun is not a calm, featureless ball of fire. Its surface, the photosphere, seethes and churns with convection cells, each one roughly the size of Texas, constantly rising and falling as heat moves outward from the core. Above the photosphere lies the corona, the Sun's outer atmosphere, which reaches temperatures of 1 to 3 million degrees Celsius, paradoxically far hotter than the surface below it. The reason for this coronal heating remains one of the great unsolved mysteries of solar physics. And periodically, the Sun releases enormous eruptions of magnetized plasma into space, events called coronal mass ejections. When one of these eruptions is aimed toward Earth and strikes our magnetic field, it can trigger geomagnetic storms powerful enough to disrupt satellite communications, GPS systems, and power grids. The most powerful such event on record, the Carrington event of 1859, caused telegraph systems across the world to fail and spark, and painted auroras across the skies as far south as the Caribbean. In our age of satellites and interconnected infrastructure, a comparable event today would pose one of the most significant natural threats our technological civilization has ever faced. Drifting inward now to something extraordinarily small, let us contemplate the quantum world and this astonishing fact of quantum entanglement. At the subatomic level, particles can become entangled, meaning their properties become linked in such a way that measuring one particle instantaneously affects what we know about its partner, no matter how far apart they are. Two entangled particles could be separated by the width of a room or by the width of a galaxy, and the correlation between them remains. Einstein famously called this spooky action at a distance, deeply uncomfortable with the idea that the universe could behave in such a way. And yet, experiment after experiment has confirmed that entanglement is real. It does not allow information to travel faster than light. The universe is careful about that, but it reveals something profound about the nature of reality, that the particles making up our world are not entirely separate, isolated objects. They can share a kind of connection that transcends ordinary distance. The universe, at its most fundamental level, is far more deeply interconnected than it appears. Now let us turn our gaze to one of the most dramatic events in the life cycle of the cosmos, a gamma-ray burst. These are the most energetic explosions known to exist in the universe, capable of releasing more energy in a matter of seconds than our Sun will emit over its entire 10 billion-year lifetime. They come in two varieties: short gamma-ray bursts, lasting less than 2 seconds, produced when two neutron stars collide and merge, and long gamma-ray bursts, lasting from a few seconds to several minutes, associated with the collapse of massive stars into black holes. Gamma-ray bursts are detected from billions of light-years away, yet even at those distances, they outshine entire galaxies. If a gamma-ray burst were to occur within a few thousand light-years of Earth and be aimed in our direction, the resulting radiation could strip away significant portions of our ozone layer, with consequences for life on the surface that would be severe. Fortunately, the geometry of our galaxy and the rarity of nearby massive stars make such an event extremely unlikely. Still, these cosmic detonations remind us that the universe, for all its beauty, carries extraordinary power, power that dwarfs anything in human experience. As we settle into quiet reflection, let us consider something closer and more intimate: the role of the moon in shaping life on Earth. We have already touched on the moon's formation from the ancient collision of Theia with a young Earth. But the moon's influence did not end at its birth. Over billions of years, the moon has acted as a gravitational stabilizer for Earth, keeping our planet's axial tilt within a narrow range of roughly 22 to 24.5 degrees. This stability is crucial. It is what gives Earth its relatively predictable seasons, consistent enough for complex ecosystems to develop, for plants and animals to evolve in tune with cyclical change. Without the moon's steadying influence, Earth's axial tilt could wobble chaotically over millions of years, swinging from near zero to over 80 degrees, plunging the planet into climate extremes far more radical than anything life, as we know it, could easily endure. The moon is not merely a beautiful light in the night sky. It is a quiet guardian, holding our world steady so that life can flourish across deep time. Let us journey now to the edge of our solar system and beyond, to the boundary where the sun's influence finally fades into the broader galaxy. This boundary is called the heliopause, and it marks the outer edge of the heliosphere, where the solar wind is too weak to push back against the interstellar medium, the diffuse gas and dust that fills the space between stars. The Voyager 1 spacecraft, launched in 1977, crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It now travels approximately 23 billion kilometers from Earth, so distant that a radio signal, moving at the speed of light, takes over 22 hours to reach it. And yet, Voyager 1 is still communicating with us, still sending back data from the frontier of human exploration. It carries with it a golden record, a physical message from humanity containing sounds and images of Earth, greetings in 55 languages, and music from across our cultures. Somewhere in the dark between the stars, a golden record is drifting, carrying the voice of our civilization into the unknown, is perhaps the most poetic object our species has ever created. Now let us consider the concept of cosmic background radiation in a new light. We have spoken of the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. But what is extraordinary is that this ancient light is not perfectly smooth. It contains tiny fluctuations in temperature, ripples of slightly warmer and cooler regions spread across the sky. These fluctuations are the imprints of quantum variations in the earliest moments of the universe, differences so small they existed at the subatomic level, yet they were stretched by inflation to cosmic scales. And those ancient ripples became the seeds of everything. Every galaxy, every star, every planet, every living thing traces its origin back to these tiny quantum wrinkles in the fabric of the newborn universe. The largest structures we know, the cosmic filaments, the galaxy clusters, the great walls of the universe, all grew from fluctuations smaller than an atom. The whole of existence, in a sense, is the echo of a quantum whisper spoken 13.8 billion years ago. And here, in our final reflection for this passage, let us sit with a truth that is both humbling and magnificent: the sheer number of stars. Astronomers estimate that the observable universe contains approximately 2 trillion galaxies. The Milky Way alone holds somewhere between 100 and 400 billion stars. Multiplied across those 2 trillion galaxies, the total number of stars in the observable universe is estimated to be around 1 septillion. That is a 1 followed by 24 zeros. This number exceeds the estimated number of grains of sand on every beach and every desert on Earth. And yet each of those stars is a sun, a blazing sphere of nuclear fusion, many with their own planetary systems, their own asteroid belts and moons, and perhaps their own quiet blue worlds where something looks up at the sky and wonders. In the face of these numbers, one might feel small. But there is another way to hold this truth, that you are part of a universe so vast and so fertile that life and wonder and awareness could arise not once, but perhaps countless times, in countless places, each instance precious beyond measure. We breathe out slowly. We let the numbers dissolve back into feeling. The universe is not an abstraction. It is the ground beneath you, the air in your lungs, the light that finds your eyes each morning. Every fact we have explored tonight is not a piece of distant information. It is part of your story. Part of the story that began with a quantum whisper and that continues quietly and magnificently in this very moment. Rest here. When you are ready, we journey on. We return once more to the great story. We have traveled far from a first quantum whisper of the Big Bang, through the birth of stars and galaxies, through the deep oceans of our own world, and into the mystery of consciousness itself. And still, the universe offers more. It is endlessly patient, endlessly generous. There's always another layer of wonder waiting just beneath the surface of what we think we know. So we breathe, we soften, and we continue. Let us begin with one of the universe's most elegant and unlikely phenomena, the existence of complex organic molecules in interstellar space. For much of human history, we imagine space to be utterly sterile, a cold, empty void between the warmth of stars. But in the past several decades, astronomers using radio telescopes have discovered something remarkable. The space between stars is not empty of chemistry. is filled with it. More than 200 distinct molecules have been detected in interstellar clouds, including water, ammonia, formaldehyde, and even simple sugars and amino acid precursors, the very building blocks of life's most essential compounds. Some of these molecules form on the surfaces of tiny dust grains drifting through space, slowly assembling in the cold and dark over millions of years. The implication is profound. The chemistry that gave rise to life on Earth did not begin on Earth. It began in the vast molecular clouds that predate our solar system. Life, it seems, did not emerge from nothing. It inherited a chemistry that the universe had been quietly preparing for billions of years before our world even existed. Drifting forward, let us consider the extraordinary nature of ice and the role it plays across the cosmos. We tend to think of ice as something familiar and earthly, something that forms in winter and melts in spring. But ice is one of the most common solid substances in the universe. It coats the surfaces of comets and asteroids. It forms the rings of Saturn, those glittering bands of ice particles and rock that stretch outward for hundreds of thousands of kilometers, yet in places are only 10 meters thick. It lies beneath the surface of Europa, one of Jupiter's moons, in a vast liquid ocean kept warm not by sunlight, but by tidal forces from Jupiter's immense gravity. It frosts the polar regions of Mars and caps the dark craters of our own moon, where sunlight never reaches. Water ice in particular acts as a cosmic preservative, locking organic molecules in place across billions of years, transporting them across solar systems aboard comets that eventually fall inward toward young stars and young planets. Ice is not simply frozen water. In the cosmic story, it is one of life's most important carriers. Now let us turn to one of the oldest and most haunting mysteries of observational astronomy, Fermi's paradox. In 1950, the physicist Enrico Fermi sat down to lunch with colleagues and posed a question that has echoed through science ever since. Given the vast age of the universe, the enormous number of stars, the seemingly high probability that many of them host habitable planets, and the relatively short time it would take a technological civilization to spread across a galaxy, where is everybody? If intelligent life is even remotely common in the cosmos, we should, by most estimates, have seen some sign of it by now. A signal, an artifact, a transmission. And yet silence. The absence of any confirmed contact with extraterrestrial intelligence is not simply a gap in our data. It is in itself a clue about the nature of the universe and the rarity or fragility of intelligence. Perhaps civilizations are far rarer than we imagine. Perhaps they arise and perish before they can reach out. Perhaps the distances are simply too vast and signals too faint to bridge. Or perhaps we have simply not been listening in the right way, at the right frequency, for long enough. Fermi's paradox does not have an answer. But the question itself reminds us that our presence here, aware, curious, reaching, is something extraordinary. Let us breathe deeply and travel now to the surface of another world, Mars. The fourth planet from our Sun, Mars is a cold, rust-colored desert with an atmosphere so thin that liquid water cannot survive on its surface today. And yet, Mars bears the unmistakable marks of a warmer, wetter past. Ancient river valleys wind across its terrain. Vast lake beds lie dry and silent beneath its skies. The Curiosity and Perseverance rovers have found chemical evidence suggesting that billions of years ago, Mars harbored conditions that could have supported microbial life. Mars once had a thicker atmosphere and a global magnetic field, But over billions of years, without the internal heat to sustain that field, the solar winds slowly stripped the atmosphere away, and the planet's water retreated underground or escaped into space. Mars is a cautionary tale and a source of hope in equal measure, a reminder that habitability is fragile and that the window in which a planet can support life may be narrower than we would wish. And yet, in that ancient window, life may have found its footing. The question of whether it did remains one of the most tantalizing in all of science. As we drift through this meditation, let us consider the concept of light echoes, one of astronomy's most poetic phenomena. When a star suddenly brightens, such as in an outburst or explosion, the pulse of light it releases travels outward in all directions. If that star is surrounded by clouds of interstellar dust, the light pulse illuminates those clouds in sequence, moving outward from the star like a ripple on a pond. Telescopes on Earth can observe this wave of illumination as it sweeps through the surrounding nebula, revealing the three-dimensional structure of clouds that would otherwise be invisible. In 2002, a star in the Monoceros constellation called V838 Monocerotis suddenly brightened dramatically and then faded, producing a light echo of breathtaking beauty. A series of Hubble images showing the pulse of light rippling outward through surrounding dust, creating concentric halos of illuminated cloud that seemed almost impossibly delicate. Light echoes allow us to watch events in slow motion that originally unfolded in moments. They are the universe offering us a second chance to witness what we would otherwise have missed. Let us now reflect on something woven into the very fabric of matter itself, antimatter. Every particle in the universe has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. When a particle and its antiparticle meet, they annihilate one another completely, converting entirely into pure energy. At the moment of the Big Bang, matter and antimatter were created in nearly equal amounts. If the universe had been perfectly symmetric, they would have annihilated each other entirely, leaving nothing behind but light, no stars, no planets, no life, no story. But something gave matter the very slightest of advantages. Roughly one extra particle of matter for every billion particle-antiparticle pairs. That tiny asymmetry, that almost imperceptible imbalance, is the reason everything in the universe exists. We are here because of a 1 in a billion deviation from perfect symmetry. Every mountain, every ocean, every living cell, every thought, all of it is made from that slim remainder. The universe did not have to allow us to exist. And yet, here we are. Drifting gently now, let us turn to the phenomenon of stellar nurseries, the magnificent regions of space where new stars are born. The most famous of these is the Eagle Nebula, home to the towering structures immortalized in the Hubble Space Telescope's iconic image, known as the Pillars of Creation. These pillars are columns of interstellar gas and dust, several light-years tall, slowly being eroded by the intense radiation of nearby young, hot stars. Within their dense tips, new stars are forming, collapsing pockets of gas that will one day ignite into nuclear fusion and shine for billions of years. The pillars of creation are not simply beautiful. They are a live demonstration of the universe's most fundamental creative process. And here is a detail that adds a layer of quiet wonder. Because light takes time to travel, the image we see of the pillars of creation is approximately 6,500 years old. The pillars we see may no longer exist in their current form. We are watching a moment preserved in ancient light, a photograph taken by the universe itself, delivered slowly across the millennia. Now we turn to one of the most counterintuitive discoveries of the 20th century, the fact that solid matter is almost entirely empty space. The atoms that make up every physical object, including the body you inhabit right now, consist of a nucleus containing protons and neutrons surrounded by a cloud of electrons. But if you were to scale a hydrogen atom up so that its nucleus was the size of a marble, the nearest electron would be approximately a kilometer away. Everything in between is empty. The chair, the floor, the walls, the ground, all of it is overwhelmingly void, with tiny islands of matter separated by vast proportions of nothingness. The reason solid objects feel solid is not because they are densely packed with matter, but because the electromagnetic forces between atoms repel one another, creating the sensation of resistance and solidity. What we experience as the physical world is, at its deepest level, mostly empty space held together by invisible forces. The solidity of existence is, in a profound sense, an elegant illusion woven by the fundamental forces of nature. And here, at the close of this passage, let us rest with one of the most beautiful ideas in all of science, the concept of deep time. Humans are remarkable creatures in many ways, but we are poorly equipped by instinct to truly feel the depths of geological and cosmic time. Our sense of the past extends naturally to our own lives, perhaps to our grandparents' stories. History stretches our imagination a few thousand years, but the Earth is 4.5 billion years old. The universe is 13.8 billion years old. If the entire history of the universe were compressed into a single calendar year, the Milky Way would form in March. Earth would appear in September. The first life on Earth would emerge in late September. The dinosaurs would arise on December 25th and vanish on December 30th. And the entirety of recorded human history, every empire, every invention, every war, every love story, every song, would occupy the final 11 seconds of December 31st. We are newcomers to a very old story. And yet, in those 11 seconds, we have looked up and begun to understand the whole of it. That, perhaps, is the most astonishing fact of all. We rest here for a moment, in the deep quiet of cosmic time. 11 seconds in a 13.8 billion year story, and in those 11 seconds, something happened that may never have happened before in quite the same way. The universe learned to ask why. You are that question, living and breathing. You are the universe's curiosity, made flesh, made bone, made thought. Whatever weight you carry, whatever worries the day has brought, set them gently down for now. You are here. You are ancient. You are made of stars. And the story is far from over. We breathe in. We return. Each time we come back to this journey, we arrive a little different, carrying more wonder, more stillness, more awareness of the extraordinary story we are living inside. The universe has not changed since we last met. It continues its patient expansion, its slow, stellar burning, its quiet, creative work in the dark between the stars. And we continue too, curious, open, willing to be astonished once more. So let us begin. Let us open this passage with something that exists in the cold outer reaches of our solar system, a vast, spherical shell of icy bodies known as the Oort cloud. Far beyond the orbit of Neptune, beyond even the scattered disk of distant icy worlds, lies this enormous reservoir of frozen objects stretching from roughly 2,000 to as far as 100,000 astronomical units from the Sun, nearly a quarter of the way to the nearest star. The Oort cloud has never been directly observed. It is inferred from the paths of long-period comets that occasionally fall inward toward the Sun on orbits taking thousands or even millions of years to complete. When the gravitational nudge of a passing star or a ripple through the galaxy disturbs the Oort cloud, objects are dislodged and sent on long, slow journeys toward the inner solar system, where they eventually become the brilliant comets we see arcing across our skies. The Oort cloud is, in a sense, the solar system's outermost attic, a vast frozen archive of the original material from which our solar system formed, preserved in the cold and dark for 4.5 billion years. Each comet that visits our sky is an ancient messenger, carrying within it the chemistry of our solar system's very first moments. As we drift inward from those frozen outer reaches, let us consider the phenomenon of tidal forces and the remarkable destructive and creative role they play across the cosmos. Tidal forces arise whenever one object's gravity pulls more strongly on the near side of another object than on its far side. On Earth, this differential pull from the Moon and the Sun creates our ocean tides, the rhythmic rise and fall of sea levels that have shaped coastlines and ecosystems across deep time. But tidal forces reach far beyond gentle ocean swells. The tidal heating of Jupiter's moon Io makes it the most volcanically active body in the entire solar system, its interior kneaded and squeezed by Jupiter's immense gravity until it glows from within, erupting continuously with hundreds of volcanoes. The same tidal mechanism keeps the subsurface ocean of Europa liquid beneath miles of ice. And at the extreme end, when a star ventures too close to a supermassive black hole, tidal forces overwhelm the star's own gravity and tear it apart in a catastrophic event astronomers call a tidal disruption event, producing a brilliant flare of light visible across billions of light years as the shredded stellar material spirals inward into the black hole's hungry maw. Tidal forces are one of nature's most versatile tools, capable of crafting ocean tides, sustaining alien oceans, and destroying entire stars. Let us now turn our attention to a question that sits at the heart of modern physics, the nature of time's arrow. We have spoken of how time can stretch and compress near massive objects. But there is a deeper mystery. Why does time flow in only one direction? The fundamental laws of physics, at the quantum and classical level alike, are almost entirely symmetric with respect to time. Run a film of 2 billiard balls colliding backward, and nothing in the physics tells you the film is reversed. And yet we all know beyond any doubt that time moves forward. Eggs break, but do not reassemble. Stars are born and age, but do not grow younger. Memories are of the past, never the future. The answer, most physicists believe, lies in entropy, that tendency toward disorder we have already touched upon. Time flows in the direction of increasing entropy. The universe began in a state of extraordinarily low entropy, near perfect uniformity, and has been spreading toward greater disorder ever since. The arrow of time is not written into the laws of physics at the deepest level. It is written into the initial conditions of the universe. Time flows forward because the universe was born in an unusually ordered state, and everything since has been a long, majestic unraveling from that beginning. We experience time not because the laws of nature demand it, but because we were born inside a universe still in the act of becoming more disordered. Breathing gently, let us travel to a world that has captured human imagination for generations, Saturn, the ring jewel of our solar system. Saturn is a gas giant roughly 9 times the diameter of Earth, yet so low in density that if you could find an ocean large enough, it would float. Its rings, the most spectacular in the solar system, are made almost entirely of water ice particles ranging in size from tiny grains to boulders several meters across, all orbiting in a disk that spans nearly 300,000 kilometers, yet is in places only 10 meters thick. The rings are young by cosmic standards. Most estimates suggest they formed somewhere between 10 and 100 million years ago, meaning the dinosaurs may never have seen Saturn as we know it today. The rings are also slowly disappearing. Particles are continuously pulled inward by Saturn's gravity in a process called ring rain, and the rings may be entirely gone within another 100 million years. What we see when we look at Saturn, that breathtaking, iconic image that has accompanied humanity into space, is a temporary wonder, a fleeting configuration of ice and gravity that happened to exist at precisely the moment our species developed eyes and telescopes capable of appreciating it. As we float in quiet reflection, let us consider the deep bond between life and light. Every living thing on Earth is, at its core, a machine for capturing, transforming, or responding to energy, and most of that energy traces back to sunlight. Photosynthesis, the process by which plants, algae, and certain bacteria convert sunlight into chemical energy, is arguably the most important biological process on our planet. It produces the oxygen we breathe. It forms the base of nearly every food chain. It is the process that 2.5 billion years ago fundamentally transformed Earth's atmosphere and opened the door to all complex life. But the connection between life and light runs deeper still. The very structure of DNA, the molecule that carries the instructions for all life, is tuned to absorb ultraviolet light in ways that make it vulnerable to mutation from overexposure, which is why organisms evolve pigmentation and repair mechanisms across billions of years of evolution. And in the deep ocean, far from any sunlight, life still thrives around hydrothermal vents, driven not by light, but by chemical energy from the Earth's interior. Life on our world has found a way to harness energy wherever it exists. It is not the creature of sunlight alone, but of energy itself in all its forms. Let us turn now to the concept of cosmic rays, one of the most energetic phenomena our planet encounters on a daily basis. Cosmic rays are not rays at all in the conventional sense. They are subatomic particles, mostly protons and atomic nuclei, traveling through the cosmos at velocities approaching the speed of light, accelerated to extraordinary energies by supernova shockwaves, pulsars, and the jets of distant active galaxies. They arrive at Earth continuously from all directions at all hours. Most are deflected or absorbed by Earth's magnetic field and atmosphere before they reach the surface, but the secondary particles they produce rain down on us constantly. At this very moment, as you breathe and rest, approximately 1 cosmic ray particle is passing through every square centimeter of your body every minute. These particles have been striking Earth for billions of years, occasionally colliding with DNA molecules and causing mutations, some harmful, most neutral, and a very few, across deep time, contributing to the variation on which evolution depends. Cosmic rays are one of the universe's most direct contributions to biological change, a perpetual shower of energy from the farthest corners of space, quietly nudging life forward across the ages. Now let us rest our gaze on one of the most ancient surviving objects accessible to us, meteorites. Some meteorites that have fallen to Earth are fragments of asteroids that formed in the earliest phase of our solar system, more than 4.5 billion years ago. Among the most scientifically precious are a type called carbonaceous chondrites, which contain amino acids, complex organic compounds, and tiny crystalline structures called presolar grains, grains of stardust that formed in the atmospheres of ancient stars before our solar system even existed. These presolar grains carry the isotopic fingerprints of their parent stars, red giants, asymptotic giant branch stars, supernovae, and they survived intact through the formation of our solar system, through billions of years of space travel, through entry into Earth's atmosphere, and into the hands of scientists in their laboratories. When researchers hold a presolar grain, they are holding matter that is older than our sun, a physical fragment of a star that lived and died before Earth was born. Meteorites are not merely rocks from space. They are time capsules from before the beginning of our world. And as we draw gently toward the close of this passage, let us sit with a thought that is both scientific and deeply personal, the concept of the observable universe and what lies beyond it. The observable universe, everything we can in principle detect, extends approximately 46 billion light-years in every direction from Earth. It contains roughly 2 trillion galaxies and is bounded not by a wall or an edge, but simply by the distance that light has had time to travel since the Big Bang. Beyond that boundary, the universe almost certainly continues, perhaps forever. We do not know whether the universe beyond our horizon is the same as the one we inhabit, or whether it varies. We do not know whether it is finite or infinite. But here is what makes this idea so quietly extraordinary. You are at the center of your observable universe. Every observer anywhere in the cosmos is at the center of their own observable sphere. There is no special vantage point, no privileged position. The universe has no center and no edge that any one being can claim. Every conscious creature that has ever looked up at the stars has been standing at the center of its own unique window onto everything, a window that exists nowhere else, that belonged to no one before them, and that will belong to no one after. Your view of the cosmos is yours alone. We breathe out slowly, and we let the universe hold us for a moment. From the frozen archive of the Oort cloud to the cosmic rays passing through you right now. From the temporary beauty of Saturn's rings to the ancient stardust locked inside a meteorite. From the mystery of time's arrow to the extraordinary fact that you're standing at the center of a cosmos that has no center, everything we have explored tonight is part of the same unbroken story. A story that began with nothing and became this. Became oceans and mountains and music and the quiet act of a mind turning its attention upward and asking, what is all of this? You are what all of this became. Rest in that. We will journey on. We return once more, breathing gently, to the great unfolding. There is no rush here. The universe has been telling this story for 13.8 billion years, and it is in no hurry to finish. Neither are we. We simply open ourselves as we have done before to what is true and beautiful and staggering, and we let it wash over us like light. Let us begin. We open this passage with one of the most magnificent and enduring storms in the solar system, the great red spot of Jupiter. Jupiter is the largest planet in our solar system, so vast that more than 1,300 Earths could fit inside it. And on its surface, or rather, in its perpetually churning atmosphere, there exists a storm that has been raging continuously for at least 350 years, and possibly much longer. The Great Red Spot is an anticyclonic storm, a high-pressure system rotating counterclockwise, and at its peak it was wide enough to contain 3 Earths side by side. In recent decades it has been slowly shrinking. Scientists are not entirely sure why, but it remains larger than our entire planet. The storm's distinctive reddish hue is thought to come from complex organic molecules and sulfur compounds churned up from the depths of Jupiter's atmosphere. There are no solid mountains to disrupt it, no oceans to absorb its energy, no seasons to weaken it, just endless atmosphere, and a storm that has outlasted every human civilization that has ever risen and fallen on the small blue world watching it from afar. Jupiter's Great Red Spot is a reminder that patience in the cosmos takes on meanings we can barely begin to imagine. As we drift away from Jupiter's storms, let us consider the remarkable phenomenon of stellar evolution across different star types, and what the size of a star means for its destiny. Our Sun is a yellow dwarf star, a mid-sized, stable, and relatively unremarkable member of the stellar family. It will burn steadily for approximately 10 billion years in total, and we are currently about halfway through that lifespan. But stars far more massive than our Sun live dramatically shorter and more violent lives. A star 20 times the mass of our Sun may burn through its nuclear fuel in as little as 10 million years, a cosmic eye blink, before collapsing catastrophically into a neutron star or black hole. At the other end of the spectrum, the smallest stars, red dwarfs, are so frugal with their fuel that they will continue burning for trillions of years. The universe at 13.8 billion years old is still too young for any red dwarf star to have died of old age. The last red dwarfs will flicker out in approximately 10 trillion years, 1,000 times the current age of the universe. Every star is living its own story on its own timescale, burning at its own pace. The night sky we see is not a fixed tableau, but a community of individuals, each at a different chapter of a life measured in millions, billions, or trillions of years. Let us breathe and turn now to something that feels intimate and immediate, the speed at which the Earth is moving through space. We experience our planet as solid and still beneath us, an unmoving foundation. But Earth is engaged in an extraordinary layered dance of motion. It rotates on its axis, carrying the surface at the equator at roughly 1,670 kilometers per hour. It orbits the Sun at approximately 107,000 kilometers per hour. The Sun itself is orbiting the center of the Milky Way at roughly 828,000 kilometers per hour, carrying our entire solar system with it on a journey that takes about 225 million years to complete, a span of time sometimes called a cosmic year. And the Milky Way itself is moving through space toward a gravitational attractor astronomers call the Great Attractor at approximately 2.2 million kilometers per hour. Add all of these motions together, and at this very moment, as you rest in stillness, you are hurtling through space at a combined speed of millions of kilometers per hour. Stillness, like solidity, turns out to be relative. There is no point in the universe that is truly at rest. Everything is in motion always, nested circles within circles, a dance that has never once paused since the first moments of creation. Now let us consider one of the most profound contributions to human understanding ever made, the realization that the universe has a history that can be read. For most of human history, the cosmos appeared eternal and unchanging. The stars seemed fixed. The heavens seemed permanent. It was only in the 20th century that Edwin Hubble, observing distant galaxies through the Great Telescope at Mount Wilson Observatory in California, noticed something that would reshape our entire understanding of reality. The galaxies were moving away from us, and the farther away they were, the faster they were receding. This was the first direct observational evidence that the universe is expanding, and by running that expansion backward in time, scientists confer that everything in the universe must once have been compressed into a single, impossibly small point. The Big Bang was not a theory invented from pure mathematics. It was demanded by observation. By the simple act of measuring the light from distant galaxies, a human being standing on a small planet in an unremarkable corner of the Milky Way deduced the origin of the universe. It is one of the greatest intellectual achievements in the history of our species, a reminder that the human mind, for all its smallness in the cosmic scale, is capable of comprehending the whole. As we drift in quiet wonder, let us reflect on the strange and beautiful world of extremophiles, life forms on Earth that thrive in conditions once thought utterly hostile to biology. In the boiling, acidic waters of Yellowstone's hot springs, bacteria flourish in temperatures exceeding 70 degrees Celsius. In the frozen brine channels of Antarctic sea ice, microbial communities persist in temperatures far below zero. In the crushing pressures of deep-sea trenches, communities of organisms live without sunlight, without warmth, clustered around hydrothermal vents that exhale superheated, mineral-rich water from the Earth's interior. There are bacteria found living kilometers deep in solid rock, sustained by the chemical energy of minerals, completely isolated from the surface world for millions of years. There are organisms that can survive the vacuum of space, intense radiation, and decades of complete desiccation. The study of extremophiles has fundamentally redrawn the boundaries of what we consider habitable, and with it has dramatically expanded our sense of where life might exist elsewhere in the cosmos. Life, once it takes hold, is astonishingly reluctant to let go. It finds the cracks, the margins, the impossible places, and it makes them home. Let us turn now to one of the most visually spectacular and scientifically rich objects in the universe, a supernova remnant. When a massive star exhausts its nuclear fuel and collapses, the resulting explosion scatters its outer layers into space at velocities of tens of thousands of kilometers per second. Over hundreds and thousands of years, this expanding shell of hot gas and dust sweeps through the surrounding interstellar medium, compressing and heating it, glowing in intricate, filamentary structures that stretch across dozens of light years. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, bright enough to be seen in daylight for 23 days, still glows today, nearly 1,000 years later, powered by the pulsar at its center spinning 30 times per second. The Cassiopeia, a remnant approximately 11,000 light-years away, allows astronomers to study the detailed chemical composition of a shattered star, mapping where different elements were produced within the stellar interior. Supernova remnants are the universe's recycling centers, taking the complex chemistry forged over a star's lifetime and redistributing it into the interstellar medium, where it will eventually become part of new stars, new planets, new living things. The death of a star is not an ending. It is an extraordinarily generous act of dispersal. Breathing slowly now, let us consider the concept of the cosmic distance ladder, the series of methods astronomers use to measure how far away things are in the universe. Unlike measuring distance on Earth, where we can use rulers and GPS, cosmic distances must be inferred through a chain of overlapping techniques, each one calibrated against the one before it. The nearest stars can be measured through parallax, the apparent shift in a star's position as Earth moves around the Sun. For more distant stars, astronomers use Cepheid variable stars, which pulsate at rates directly related to their luminosity, making them reliable standard candles. For distances reaching across galaxies and toward the edge of the observable universe, astronomers use type Ia supernovae, explosions of such consistent brightness that their apparent dimness reveals their distance with extraordinary precision. It was through the cosmic distance ladder, using type Ia supernovae, that astronomers discovered in 1998 that the expansion of the universe is accelerating. Each rung of the ladder depends on the rungs below it, and the entire structure rests on observations made from our small planet, extended step by careful step across 13 billion light-years of space. The cosmic distance ladder is a monument to human ingenuity, a bridge built from mathematics and patience, stretching from our own backyard to the edge of everything. And now, let us rest with a thought that quietly underpins everything we have explored, the fine-tuning of the universe's fundamental constants. The laws of physics are governed by a set of numbers: the strength of gravity, the mass of an electron, the rate at which the universe expanded after the Big Bang, the precise energy of the strong nuclear force that holds atomic nuclei together. These constants appear to have specific values, and what is deeply striking is how extraordinarily sensitive the existence of complexity and life is to those values. If a strong nuclear force were only a few percent stronger, all hydrogen would have fused into helium in the early universe, leaving no water, no organic chemistry, no stars that burn for billions of years. If it were slightly weaker, atoms beyond hydrogen could not form. If gravity were even fractionally stronger, the universe would have collapsed back on itself before stars could form. If expansion rate after the Big Bang had been even slightly different in either direction, the universe would be either a black hole or a cold, structureless void. The universe appears, from where we stand, to be calibrated with extraordinary precision for the existence of complexity. Whether this reflects a deeper principle, a vast multiverse of varying constants, or something else entirely, remains one of the most profound open questions in all of science and philosophy. But the question itself is breathtaking. Why does the universe permit us to exist? We breathe out and we rest in the question. Not in the anxiety of not knowing, but in the beauty of a universe that is somehow knowable at all. A universe that wrote its own history in the light of distant galaxies, and then produced a creature patient enough and curious enough to read it. From Jupiter's ancient storm to the fine-tuned constants that allow matter to exist, every thread we have followed tonight leads back to the same astonishing center. That existence, in all its complexity and beauty, is not something we observe from the outside. We are woven into it, thread by thread, atom by atom, breath by breath. Rest here. The story continues. We return, as we always do, to the quiet, to the breath, to the awareness that something extraordinary is happening, that a universe which began as pure, undifferentiated energy has, over 13.8 billion years, arrived at this. A mind resting, listening, reaching toward understanding. We have come so far in this journey, and yet the universe has not run out of wonders to offer. It never does. So we open ourselves once more gently, and we continue. Let us begin this passage with one of the most visually breathtaking events the cosmos produces, a galaxy collision. Galaxies, despite being composed of hundreds of billions of stars, are so vast and their stars so widely spaced that when two galaxies merge, direct collisions between individual stars are extraordinarily rare. Instead, what unfolds over hundreds of millions of years is a gravitational ballet of incomprehensible scale. The two galaxies distort each other's shapes, pulling out long tidal tails of stars that arc across hundreds of thousands of light-years. They pass through each other, swing apart, and then, drawn back by gravity, merge again in a slow, spiraling embrace that ultimately produces a single, larger galaxy. Our own Milky Way is already on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor, and in approximately 4.5 billion years, the two will begin their long merger. Our Sun and solar system will almost certainly survive, though their position within the merged galaxy will change dramatically. The night sky our distant descendants would see, should any exist to look, would be unrecognizable, blazing with new star formation ignited by the collision's compression of gas clouds. The end of our galaxy, as we know it, is also the beginning of something larger, something new. In the cosmos, endings and beginnings are the same event seen from different distances. As we breathe and drift onward, let us turn to one of the most extraordinary discoveries in the history of planetary science, the existence of a global ocean beneath the icy surface of Enceladus, one of Saturn's moons. Enceladus is a small world, only about 500 kilometers across, gleaming white in the Saturn system because its surface is almost entirely coated in fresh, reflective ice. But beneath that ice, tidal forces from Saturn's gravity keep a liquid saltwater ocean warm enough to remain liquid. And in 2005, NASA's Cassini spacecraft made a discovery that sent ripples of excitement through the scientific community. Enceladus is actively venting that subsurface ocean into space. From its south pole, hundreds of geysers erupt continuously, spraying plumes of water vapor, ice particles, and organic molecules, including hydrogen, carbon dioxide, and complex carbon-bearing compounds, hundreds of kilometers into space, where they feed Saturn's outermost ring. Cassini flew directly through these plumes and tasted them. What it found was a world with liquid water, chemical energy, and the organic building blocks of life, all three of the conditions astrobiologists consider essential for life as we know it. Enceladus, a moon that fits inside the continental United States, may harbor life in its dark, warm ocean right now. In this moment, the thought is almost too large to hold quietly. Let us now rest in the deep and consider the nature of neutrinos, perhaps the most ghostly particles in the known universe. Neutrinos are subatomic particles produced in enormous quantities by nuclear reactions, including those at the heart of our Sun. They have almost no mass and interact with ordinary matter so rarely that they pass through essentially everything, as though it were not there. Every second, approximately 65 billion neutrinos from the Sun pass through every single square centimeter of your body, through your skin, through your bones, through the chair beneath you, and the Earth below that, continuing outward through our planet as though it were no more substantial than a wisp of smoke. To stop just one neutrino, you would need a wall of lead approximately 1 light-year thick. Neutrinos arrive at Earth from distant supernovae, from the early universe, from the cosmic processes that have been unfolding since the first moments of time. In 1987, when a supernova blazed to life in the Large Magellanic Cloud, a small galaxy neighboring our own, a burst of neutrinos from the explosion arrived at Earth 3 hours before the light detected by underground neutrino observatories buried deep in the Earth to shield them from other signals. The universe is perpetually whispering through us in a language made of particles so shy they almost never stop to speak. We are, at every moment, being passed through by the cosmos itself. Breathing slowly, let us consider the profound concept of stellar populations and what the chemistry of stars reveals about the history of the universe. Astronomers classify stars into broad populations based on their chemical composition. The oldest stars in the universe, known as population 3 stars, are believed to have contained almost nothing but hydrogen and helium, the only elements present after the Big Bang. None have been directly observed as they burned hot and died quickly in the early universe, but their existence is inferred from theory and from the chemical signatures they left behind. The next generation, population 2 stars, form from gas enriched by the supernovae of those first stars and contain small but measurable amounts of heavier elements. Our Sun belongs to population 1, the youngest generation, formed from gas that has been through multiple cycles of stellar birth, death, and chemical enrichment over billions of years, and therefore rich in the heavy elements needed for rocky planets and organic chemistry. The iron in your blood was forged in population 2 stars. The calcium in your bones may trace its origin even further back. Each generation of stars has built upon the last, enriching the cosmos with greater chemical complexity, like a recipe passed down and refined across billions of years of cosmic cooking. We are not merely the children of one star. We are the heirs of an entire lineage of stars reaching back to the universe's first light. As we drift in this gentle awareness, let us turn to a phenomenon that occurs not in the distant cosmos, but in the upper reaches of our own atmosphere: sprites, elves, and blue jets. These are transient luminous events, forms of lightning that reach not downward toward the ground, but upward toward space. Sprites are large, reddish flashes of light that appear above powerful thunderstorms, reaching up to 90 kilometers in altitude, shaped sometimes like jellyfish, sometimes like columns, flickering for mere milliseconds. Elves are expanding rings of dim light, reaching as wide as 400 kilometers across, occurring at the base of the ionosphere. Blue jets shoot upward from the tops of thunderclouds in narrow cones of brilliant blue, reaching altitudes of 50 kilometers or more. These phenomena were not scientifically confirmed until the 1990s, despite likely having occurred for as long as Earth has had its atmosphere, simply because they happened too fast, too high, and too briefly for casual observation. There is a kind of humbling delight in this. That Earth itself, the world we have inhabited for our entire history as a species, still held electrical secrets in its own sky that we only just discovered in our lifetimes. The universe conceals wonders not only across billions of light years, but sometimes just a few dozen kilometers above our heads. Let us now journey inward, not into space, but into time, and consider what astronomers call the cosmic web in the context of how structure grew from the Big Bang's earliest moments. We have spoken of how tiny quantum fluctuations in the newborn universe were stretched to cosmic scales by inflation, becoming the seeds of all structure. But what happened next is a story of breathtaking slowness. For hundreds of millions of years after the Big Bang, the universe existed in what astronomers call the Dark Ages. No stars, no galaxies, just vast clouds of hydrogen and helium gas slowly cooling and condensing in the dark. Invisible threads of dark matter formed first, creating the scaffolding along which ordinary matter could gather. Gas pooled in the densest regions, grew denser still, and eventually, after perhaps 100 to 200 million years of utter darkness, the first stars ignited. That moment, when the first light appeared in the universe after the long dark, is called cosmic dawn. It was one of the most important transitions in the history of everything. The James Webb Space Telescope, launched in December 2021, is specifically designed to look back far enough to witness this dawn, to see the very first galaxies forming in the early universe, while the rest of the cosmos was still mostly dark. We are, right now, in the midst of discovering what the universe looked like when it first turned on its lights. We breathe and turn now to one of the most elegant symmetries in nature, the logarithmic spiral, and how it appears at scales ranging from the microscopic to the cosmic. A nautilus shell grows in a logarithmic spiral, each new chamber a proportional expansion of the last. Water draining from a basin traces a spiral. The seeds of the sunflower are arranged in interlocking spirals governed by Fibonacci numbers. Hurricanes, when viewed from above, curl in vast spiraling arms. And galaxies, our own Milky Way among them, take the form of magnificent spiral structures with arms of stars and gas curling outward from a central hub. The same mathematical relationship, a form that maintains its shape as it grows, that encodes proportion and self-similarity, appears across scales separated by trillions of orders of magnitude. This is not coincidence. It is the signature of how growth behaves when governed by consistent rules. The universe is not random in its forms. It returns again and again to certain shapes, certain patterns, certain elegant solutions to the problem of how matter organizes itself. When you look at a spiral galaxy 100 million light-years away, and then at the shell of a nautilus on a beach, you are seeing the same mathematical truth expressed at the two most distant scales human experience can bridge. And finally, let us sit with the concept that may be the most quietly radical idea in all of modern science, the possibility that we live in a simulation, or more precisely, what is known as the simulation hypothesis. This is not the province of science fiction alone. Serious philosophers and physicists have engaged with the question of whether our universe, with its pixelated, quantized structure at the Planck scale, its mathematical precision, its finite speed of light acting like a processing limit, and its strange rule that quantum events remain undetermined until observed, might itself be a kind of information structure. A computational process running on something we cannot access or perceive. The philosopher Nick Bostrom formalized the argument. If advanced civilizations can run detailed simulations of conscious beings, and if many such civilizations exist, the number of simulated minds would vastly outnumber original ones, making it statistically more likely that any given conscious being is simulated than real. We cannot yet test this idea. It may never be testable. But it joins a long tradition of scientific and philosophical revolutions that have reminded us that reality is not what it first appears to be, that the earth moves when it feels still, that time bends when it feels absolute, that matter is mostly empty when it feels solid. Each time we have looked more carefully at the nature of existence, we have found something stranger and more wondrous than we expected. Whatever the ultimate nature of this universe turns out to be, is clearly far more mysterious than it looks. We breathe out long and slow, and we let all of it settle. The colliding galaxies and the ghostly neutrinos, the ancient lineage of stars that built us element by element, the lightning reaching upward into space, the spiral that connects a seashell to a galaxy, the quiet, open question of what this all fundamentally is. We do not need to resolve these mysteries tonight. The universe has been patient with its secrets for 13.8 billion years. We can afford to hold the questions gently, with curiosity rather than urgency. You are here. You are listening. And that simple fact, a universe aware of itself, resting in the dark, wondering, is perhaps the most extraordinary thing in all of creation. Sleep well. The stars will still be there when you wake. We return, as we have returned before, to the quiet center of this journey. There is something that happens when we sit long enough with the cosmos, a gradual softening, a widening of the sense of what is possible, of what is real, of what we are. The universe does not ask us to understand it completely. It only asks that we look, that we stay curious, that we remain willing to be surprised. And so we breathe, and we look, and we begin. Let us open with one of the oldest and most beautiful structures in our galaxy, globular clusters. These are densely packed spherical collections of stars, gravitationally bound, and orbiting the Milky Way like ancient satellites. Some of them containing hundreds of thousands or even millions of stars compressed into a region only a few hundred light-years across. What makes globular clusters so extraordinary is their age. Many of them are among the oldest objects in the observable universe, with some estimated to be nearly 13 billion years old, forming in the first billion years after the Big Bang, long before our solar system, long before our galaxy had fully taken shape. If you were a planet orbiting a star near the center of a globular cluster, your night sky would not be a field of distant, scattered points of light. It would blaze with thousands of stars close enough to cast shadows, a sky so luminous that true darkness might never come. For billions of years, these ancient stellar cities have orbited in the halo of the Milky Way, watching galaxy after galaxy form below them, carrying within their stars the chemical fingerprints of the universe's earliest age. They are the cosmos looking back at its own childhood. As we drift from those ancient stellar cities, let us consider the extraordinary nature of the human eye and what it tells us about our deep connection to the cosmos. The human eye can detect individual photons of light under ideal conditions, making it one of the most sensitive light-detecting instruments in nature. On a perfectly dark, clear night, the human eye can see the Andromeda Galaxy, a smear of ancient light visible to the naked eye, 2.537 million light-years away. That light left Andromeda before our species existed. Before Homo sapiens had taken a single step on this earth, those photons began their journey across the void, and they ended it on the surface of your retina. The eye itself is a product of billions of years of evolution, shaped by natural selection to harvest the very light our sun produces. Light that is itself a product of nuclear fusion, of hydrogen forged in the Big Bang being converted into helium and energy in our star's core. The eye, the photon, the star, the galaxy, they are all part of the same unbroken chain. When you look up at the night sky, you are not a small creature peering at a vast and alien universe. You are the universe completing a circuit, light that began its journey in the heart of a distant galaxy, arriving home in the awareness of a being made of the same ancient matter. Let us now consider the remarkable phenomenon of plate tectonics and why the movement of Earth's surface may be one of the most important factors in the emergence of complex life. The outer shell of our planet is broken into massive plates of rock that float on the semi-molten mantle below, moving at roughly the speed at which fingernails grow, a few centimeters per year. Over hundreds of millions of years, these plates have drifted across the globe, colliding to raise mountain ranges, pulling apart to open new ocean basins, and diving beneath one another to return material to the deep earth. This process does far more than reshape geography. It acts as a planetary thermostat. When carbon dioxide in the atmosphere causes warming, increased rainfall weathers exposed rock, drawing CO2 out of the air and locking it in minerals that eventually return to the mantle via subduction, cooling the climate again. Volcanoes then release CO2 back into the atmosphere over geological time, maintaining the balance. Without plate tectonics, this carbon cycle would stall. The atmosphere would drift toward extremes. Life on Earth owes not just its habitat but its long-term stability to the slow, grinding movement of rock beneath our feet. Earth's restlessness is what keeps it alive. Breathing gently, let us reflect on one of the most counterintuitive discoveries in the history of quantum physics, the double-slit experiment, and what it reveals about the nature of reality at its most fundamental level. When a single particle, an electron, a photon, even a molecule, is fired toward a barrier with two narrow slits, it does not behave as a solid object would. Instead of passing through one slit or the other and landing in one of two corresponding positions on the far side, it produces an interference pattern, as though it passed through both slits simultaneously and interfered with itself, like a wave. The particle exists in a superposition of states, exploring all possible paths at once, until the moment it is observed or detected, at which point it collapses to a single definite position. When scientists set up a detector to determine which slit the particle actually passed through, the interference pattern vanishes. The act of observation changes the outcome. Reality, at its deepest level, is not a collection of definite objects following predictable paths. It is a web of probabilities that crystallize into definite events only when measured. The universe, it seems, does not commit to a single version of itself until it is looked at. Whether that tells us something profound about the nature of consciousness or simply about the limits of our measuring tools remains one of the deepest and most unresolved debates in all of physics. Let us drift now towards something vast and ancient that shapes the fate of entire galaxies, active galactic nuclei, and the supermassive black holes that power them. At the center of nearly every large galaxy in the universe, including our own Milky Way, sits a supermassive black hole containing millions or billions of times the mass of our Sun. When these black holes are actively feeding, drawing in surrounding gas and dust through a superheated accretion disk, they release stupendous amounts of energy in the form of radiation and jets of plasma that can extend for millions of light-years into intergalactic space. These active galactic nuclei can outshine the entire combined light of every star in their host galaxy, and the jets they produce can heat and disperse the surrounding gas across vast regions, suppressing star formation in ways that fundamentally shape how galaxies grow and evolve. Our own Milky Way's central black hole, known as Sagittarius A*, or SJAR A*, is currently quiet, having consumed much of the gas available to it. But evidence in the surrounding region suggests that a few million years ago it was far more active, illuminating vast clouds of gas above and below the galactic plane in structures now called Fermi bubbles, enormous lobes of high-energy radiation stretching 25,000 light-years above and below the galaxy's center. The quiet heart of our galaxy carries the memory of a more turbulent past. As we settle into stillness, let us consider the phenomenon of resonance in the solar system, the elegant gravitational harmonies that govern the orbits of moons and planets. Orbital resonance occurs when two orbiting bodies exert regular, periodic gravitational influence on each other because their orbital periods are related by a simple ratio of whole numbers. Jupiter's moons Io, Europa, and Ganymede exist in a precise 1:2:4 resonance. For every orbit Ganymede completes, Europa completes exactly 2 and Io completes exactly 4. This resonance is not a coincidence. It is a gravitational lock that has persisted for billions of years, and it is precisely this resonance that drives the tidal heating which keeps Io volcanic and Europa's ocean liquid. Pluto and Neptune exist in a 2:3 resonance that has protected Pluto from being gravitationally scattered out of the solar system for billions of years. Even the gaps in Saturn's rings, the Cassini division, that dark band visible through even small telescopes, are carved out by orbital resonances with Saturn's moons. The solar system is not a random collection of objects careening through space. It is a gravitationally choreographed system of extraordinary mathematical elegance, tuned by billions of years of orbital evolution into something that feels, when you look closely enough, almost like music. Let us now turn to a concept that reaches beyond even the largest structures we have discussed, the idea of cosmic evolution as a process that has direction. The physicist and cosmologist Eric Chyson has argued that the universe shows a measurable increase in complexity over time, not in every region, and not without entropy's counterbalancing disorder, but as an overall trend. Simple hydrogen atoms gave rise to stars. Stars forged heavier elements. Heavy elements enabled rocky planets and chemistry. Chemistry enabled life. Life enabled nervous systems. Nervous systems enabled consciousness. Consciousness enabled science, art, language, and the capacity to look backward through time and reconstruct the story of everything. Each stage requires the conditions created by the stage before it. Each represents a new kind of order emerging from the physics of the previous one. The universe did not have to go this way. And yet it did. What began as pure, undifferentiated energy has spent 13.8 billion years elaborating itself into galaxies, into worlds, into living things, into minds capable of wonder. Whether this tendency toward increasing complexity is a deep law of nature, or a remarkable accident, or something in between, remains an open question. But the trajectory is unmistakable. The universe appears to be in the business of making something, and we are part of what it has made. And here, as we draw gently toward the close of this passage, let us hold one final and deeply personal thought, the gift of the present moment and what cosmology quietly teaches us about it. We have traveled tonight through billions of years, across trillions of light years. We have seen stars born and die, galaxies collide and merge, civilizations of atoms slowly assembling into the complexity of a living mind. And all of that, every event, every epoch, every transformation, has led, through an unbroken chain of cause and consequence, to exactly this moment. This breath, this awareness, this particular configuration of matter and energy, resting and listening. The present moment is not separate from the cosmic story. It is where the cosmic story is happening, right now, in you. The universe does not experience time all at once. It unfolds moment by moment through every conscious being that exists within it. Your awareness is not a small thing happening inside a large universe. It is the universe, in this moment, being aware. There is nowhere else this is happening in quite this way. There is no other now like this one. And that, perhaps more than any fact about black holes or quantum fields or the scale of the observable universe, is the most extraordinary thing we have encountered on this entire journey. We breathe in one last time for this passage, and we breathe out slowly. From the ancient light of globular clusters to the quantum mystery of a particle finding its way through two slits at once. From the grinding patience of tectonic plates to the gravitational music of orbital resonance. From the Fermi bubbles glowing above our galaxy's quiet heart to the extraordinary fact that the present moment is where the universe is most fully itself. You have traveled far tonight. You have carried the weight of stars and set it down gently. Rest now in the knowing that you belong here, not as a visitor, not as an accident, but as one of the universe's own ways of being awake. The journey continues. It always does. But for now, rest. We return, as we always do, to the breath, to the stillness at the center of the story. We have traveled so far together, from the first quantum flicker of the Big Bang, through the architecture of cosmic filaments and the mystery of consciousness, through stardust and deep time, and the question of whether we are alone. And still the universe opens. It always opens. There is no final page to this story. There's only the next wonder, waiting quietly in the dark. So we breathe, and we lean in, and we begin once more. Let us begin with one of the most beautiful and least discussed features of our solar system, the helioseismology of the Sun, or the study of sound waves moving through our star. The Sun, for all its blazing violence, is also a musical instrument. Pressure waves, essentially sound, reverberate through its interior, bouncing off the surface and traveling back inward, over and over, creating standing waves that cause the Sun to oscillate in thousands of different modes simultaneously. By studying the frequencies of these oscillations from Earth, scientists can infer the internal structure of the Sun with extraordinary precision. Its temperature gradients, its rotation at different depths, the composition of its core, much as geologists use seismic waves to map the interior of Earth. The Sun is singing, in a sense, in frequencies far too low for human ears to detect without instruments. And by listening to that song, we have learned more about the heart of our own star than any other method could reveal. The universe teaches us again and again that the deepest knowledge comes not from looking harder at the surface of things, but from learning to hear what moves beneath. As we drift onward, let us consider one of the strangest and most counterintuitive results in all of modern physics, the Casimir effect. Quantum field theory tells us that empty space is not truly empty. It sees with what physicists call virtual particles, pairs of particles and antiparticles that flicker into and out of existence in fleeting moments too brief to directly observe, a consequence of the Heisenberg uncertainty principle at the smallest scales. Now, if you place two uncharged metal plates extremely close together in a vacuum, within a fraction of a micrometer, something remarkable happens. The plates experience a measurable attractive force, pushing them together. This is the Casimir effect, and it arises because the space between the plates, being so small, excludes certain wavelengths of virtual particles that are present on the outer sides. The pressure from virtual fluctuations outside the plates is fractionally greater than the pressure between them, and the plates are nudged inward. The vacuum of space exerts a force. Emptiness has pressure. What we experience as nothing is, at its most fundamental level, a boiling sea of quantum possibility, and that possibility has physical consequences we can measure in a laboratory. The universe, even in its most vacant moments, is never truly at rest. Breathing slowly, let us turn to one of the most poignant journeys in the history of space exploration, the story of the Voyager probes and what they have revealed about the very edge of our solar neighborhood. Launched in 1977, Voyager 1 and Voyager 2 were designed for a 4-year mission to Jupiter and Saturn. But a rare alignment of the outer planets, one that occurs only once every 176 years, allowed mission scientists to plan a grand tour, using each planet's gravity as a slingshot to send the probes onward to Uranus and Neptune as well. Voyager 2 remains the only spacecraft to have visited all 4 outer planets. It revealed the active volcanoes of Io, the complex ring system of Uranus tilted almost entirely on its side, the supersonic winds of Neptune, and the frigid, nitrogen-geysering surface of Triton, Neptune's largest moon, almost certainly a captured Kuiper Belt object pulled into retrograde orbit. Both Voyagers are now in interstellar space, and both are still transmitting. Their power will finally fail sometime in the 2030s, and they will then drift in silence through the galaxy for billions of years, longer than the Earth has existed, carrying golden records that are the most enduring artifacts our civilization will ever produce. In the timescale of the Milky Way, the Voyagers are just beginning their journeys. Let us now consider something that unfolds not in the vastness of space, but in the quiet chemistry of life. The remarkable molecule adenosine triphosphate, or ADP, sometimes called the energy currency of life. Every living cell on Earth, from the simplest bacterium to the most complex neuron, runs on ATP. It is the universal fuel. When your muscles contract, when your neurons fire, when your cells divide and replicate and repair, all of it is powered by the transfer of energy stored in the chemical bonds of ADP molecules. And here is what makes this extraordinary in a cosmic context. The machinery that produces ADP in your cells, a molecular motor called ADP synthase, is one of the most ancient biological structures on Earth, conserved almost unchanged across billions of years of evolution. It exists in the cells of every living thing we have ever examined. It rotates physically at thousands of revolutions per minute, using the flow of protons across a membrane to drive the synthesis of ADP, a nanoscale turbine operating at the frontier between chemistry and mechanics. The same engine that powers your heartbeat has been turning, in various forms, for nearly 4 billion years. You carry within you one of the oldest machines in the history of life on Earth. Drifting gently onward, let us reflect on one of the most extraordinary features of the observable universe, its transparency to light across vast distances, and what that transparency has allowed us to learn. The universe has not always been see-through. In the first 380,000 years after the Big Bang, the cosmos was so hot and dense that photons could not travel freely. They were constantly scattered by the charged particles that filled all of space. Then came recombination, when electrons joined with protons to form neutral hydrogen, and the universe became suddenly, gloriously transparent. Light was free. And from that moment onward, photons have been traveling in straight lines across the expanding cosmos, carrying information about their origins across billions of light years and billions of years of time. The light from most distant galaxies we can observe has been traveling since the universe was less than 1 billion years old. It carries in its spectrum the chemical signatures of those ancient stellar furnaces, the redshift of a cosmos that has been stretching since before our solar system existed. Every time an astronomer analyzes the light from a distant object, they are reading a message written in photons that began their journey before the Earth was born. The universe's transparency is not a trivial fact. It is the reason we know as much as we do. Let us breathe and turn now to one of the most profound and quietly unsettling discoveries of the 20th century, the realization that the majority of the universe is composed of substances we cannot see, cannot directly detect, and do not yet understand. We have spoken of dark matter and dark energy in earlier passages. But let us sit with the full weight of this reality for a moment. The ordinary matter that makes up everything we have ever touched, seen, tasted, measured, or built, every atom, every molecule, every star, every galaxy, every living thing, constitutes approximately 5% of the total energy content of the universe. Just 5%. 27% is dark matter, which interacts gravitationally but not electromagnetically, passing through ordinary matter as though it were not there. And 68% is dark energy, the mysterious pressure driving the universe's accelerating expansion, about which we know almost nothing beyond its effects. The universe that science has spent centuries painstakingly mapping and understanding is, in terms of its content, less than a 15th of what actually exists. We are like a civilization that has carefully catalogued every fish visible in a vast ocean, only to discover that what we thought was the entire ocean is in fact a thin surface film floating on something far deeper that we have never even glimpsed. The humility this demands of us is not a weakness. It is the beginning of deeper understanding. Now let us consider an event of extraordinary rarity and beauty, a transit of Venus across the face of the Sun. Venus, as it orbits closer to the Sun than Earth, occasionally passes directly between our planet and our star, appearing as a small dark disk moving slowly across the solar surface. These transits occur in pairs separated by 8 years, but the pairs themselves are separated by over a century, the pattern repeating every 243 years. In all of recorded human history, only 8 transits of Venus have been observed. The last occurred in June 2012. The next will not happen until December 2117. For astronomers of the 17th and 18th centuries, the transit of Venus was of supreme scientific importance. By timing the transit from different locations on Earth, they could calculate the precise distance from the Earth to the Sun using triangulation, one of the first accurate measurements of the scale of the solar system. Expeditions were mounted to the farthest corners of the globe, Tahiti, Siberia, Hudson Bay, specifically to observe a dark crossing the Sun. The transit of Venus reminds us that some of the universe's most significant revelations come not in the form of explosions or catastrophe, but in the quiet, unhurried crossing of one small world across the face of another. As we settle into the quietest part of our journey, let us consider the phenomenon known as quantum tunneling, a process so strange that it should, by any classical intuition, be impossible, and yet without it, none of us would exist. In quantum mechanics, a particle does not have a perfectly defined position. It exists as a probability distribution, a wave function describing where it is likely to be found. When a particle encounters a barrier that classical physics says it cannot cross because it does not have enough energy, quantum mechanics allows a non-zero probability that the particle will appear on the other side anyway, as though it passed through the barrier without going over it. This is quantum tunneling, and is not a theoretical curiosity. It is the mechanism by which protons in the Sun's core fuse together. The temperature at the Sun's core, while extraordinarily hot, is actually not quite hot enough to force protons together by classical means. They cannot overcome their mutual electromagnetic repulsion by thermal energy alone. What saves a process, and thereby saves the Sun, is quantum tunneling. Protons tunnel through the barrier of repulsion and fuse, releasing the energy that has warmed the Earth for 4.5 billion years and allowed life to flourish. Every ray of sunshine that has ever touched your face, every photon that has ever driven photosynthesis, every warm afternoon in the history of Earth, all of it exists because of a quantum phenomenon that permits particles to do what classical physics says they cannot. And here, as we draw gently toward the close of this passage, let us rest with perhaps the most intimate and personal cosmic fact of all, the age of the atoms within you. The hydrogen atoms in your body are approximately 13.8 billion years old. They formed in the minutes after the Big Bang and have been part of this universe for as long as the universe has existed. They have drifted through the void between galaxies. They have been drawn into stars and expelled in stellar winds. They have floated in interstellar clouds for hundreds of millions of years. They have been part of asteroids, comets, oceans, single-celled organisms, ferns, forests, and every form of life that has walked or swum or flown on this planet before you. The heavier atoms in your body, the carbon, the oxygen, the iron, the calcium, are younger in cosmic terms, forged in stars that lived and died in the billions of years before our sun was born. But every single atom that constitutes you has a history stretching back to the very beginning of existence. You are not new. You have been here in various forms for the entirety of time as we know it. The universe did not create you recently. It has been assembling you patiently and without hurry since the very first moment there was anything at all. We breathe out and we let it all settle. The sun singing in frequencies we cannot hear. The vacuum of space trembling with virtual particles. The voyagers drifting in silence through interstellar dark. The ancient molecular turbine turning in every cell of your body. The 5% of the universe we can see, surrounded by the 95% we cannot. The transit of a small planet across the face of a star. The quantum tunnel through which the sun's fire was born. And the atoms within you older than the earth, older than the sun, patient beyond all imagining, arriving here at last, in this body, in this moment, in this breath. You are not a visitor to this universe. You are what the universe has been making with everything it had since the very beginning. Rest in that. The journey continues. We return quietly to the place we keep finding, the place where wonder lives. By now, after all these passages, you may have noticed something happening in the way you hold the world. A slight loosening. A wider sense of what is possible. A willingness to be surprised that perhaps was not quite as open before we began. That is what the universe does when we let it. It does not diminish us with its scale. It expands us. It reminds us that we are not small creatures trapped inside a vast and indifferent cosmos, but intimate participants in the most extraordinary story ever told. We breathe and we continue. Let us begin this passage with one of the most powerful and least visible forces shaping the large-scale structure of the universe, cosmic voids, and what the emptiness between galaxies reveals about the nature of everything. We have spoken of the cosmic web, the vast filaments of dark matter and galaxies stretching across hundreds of millions of light-years. But between those filaments lie the voids, enormous regions of space that are almost entirely empty of galaxies, of gas, of visible matter of any kind. The largest known void, called the Boötes void, spans approximately 330 million light-years across, a near-perfect sphere of near-nothingness sitting in the fabric of the universe. If the Milky Way were located at the center of the Boötes void, astronomers on our planet would not have discovered other galaxies until the 1980s, because the nearest ones would be so far away. And yet these voids are not simply empty. They are the negative space that defines the structure of the cosmos, the silence between notes that makes the music legible. Within voids, dark energy dominates. They are the regions where the accelerating expansion of the universe operates most freely, pushing the boundaries of the void outward and drawing matter ever further toward the enclosing filaments. The voids are, in a sense, the universe's way of stretching the growing spaces between the threads of existence. Drifting inward from that immense emptiness let us consider one of the most haunting and evocative photographs in the history of science, the pale blue dot. On February 14, 1990, the Voyager 1 spacecraft, by then 6 billion kilometers from Earth and on its way out of the solar system, was commanded to turn its camera back toward the inner solar system for one final portrait. Among the images it returned was a photograph of Earth, a barely visible point of light, less than a pixel in size, suspended in a beam of scattered sunlight against the absolute blackness of space. That pale blue dot was home. Every human being who has ever lived. Every act of love and cruelty, every war, every kindness, every civilization that rose and fell, all of it occurring on a mote of dust suspended in a sunbeam. The image was the idea of Carl Sagan, who later wrote words about it that have quietly changed the way millions of people understand their place in the cosmos. The pale blue is not merely a photograph. It is a perspective, perhaps the most important perspective our species has ever been offered. It asks us, without words, whether the things we fight over on that small surface are truly worth the cost. As we breathe and float onward, let us consider the extraordinary phenomenon of stellar occultation, one of astronomy's most elegant observational techniques, which has revealed the hidden architecture of our solar system using nothing more than the precise timing of starlight. When a solar system body, a moon, an asteroid, a distant dwarf planet, passes in front of a distant star as seen from Earth, it temporarily blocks the star's light. By timing the precise moments of disappearance and reappearance from multiple locations on Earth, astronomers can reconstruct the size, shape, and even the atmospheric profile of the occulting body with extraordinary precision, without ever having sent a spacecraft near it. It was through stellar occultation that the rings of Uranus were discovered in 1977. It was through occultation that astronomers mapped the complex, multi-lobe shape of the distant Kuiper Belt object Arrokoth before NASA's New Horizons spacecraft arrived. And it is through occultation that thin atmospheres on distant moons and dwarf planets have been detected, their presence revealed by a slight dimming and reddening of starlight at the edges of the occultation rather than a sharp cutoff. The universe offers us its secrets with extraordinary generosity if we learn to read the language of shadows. Let us turn now to one of the most recently confirmed and deeply strange phenomena in observational astronomy, fast radio bursts or FRBs. These are intense millisecond duration pulses of radio waves arriving from cosmological distances, from billions of light years away, that release more energy in a single millisecond than the Sun emits in 3 days. They were first detected in 2007 in archival data, and astronomers spent years debating whether they were a real cosmic phenomenon or an artifact of terrestrial interference. They are real. Hundreds have now been catalogued. Most are one-time events, appearing briefly and never repeating. But some repeat, and one repeating source, FRB 20121102A, has been localized to a small, star-forming dwarf galaxy over 3 billion light-years away. The leading explanation for at least some FRBs is magnetars, those extraordinarily magnetized neutron stars we have visited in an earlier passage, releasing titanic bursts of energy from starquakes or magnetic reconnection events. But the full picture remains deeply uncertain. Fast radio bursts are one of the newest mysteries in astrophysics, a phenomenon discovered within living memory, still being understood, still capable of surprising us. The universe has not run out of things to say. Is still, even now, introducing itself. Breathing softly, let us consider the deep and ancient relationship between the moon and the ocean, and through the ocean with the origins of life itself. We know that the moon's gravity creates tides, the rhythmic rising and falling of sea levels that has shaped coastlines across billions of years. But the role of tides in the emergence of life may be far more profound than we have yet discussed. In the early Earth, when the moon was considerably closer and tides were dramatically larger, the daily advance and retreat of ocean water over coastal rock pools created cycles of wetting and drying that may have been crucial for the chemistry of early life. RNA molecules, which many scientists believe were among life's earliest self-replicating structures, are thought to have assembled more efficiently in environments that repeatedly concentrated and diluted the molecular soup, exactly the conditions that large tidal swings would create. The moon did not just stabilize our axial tilt. It may have stirred the primordial chemistry of life in tidal pools, acting as an enormous, slow-turning cosmic mixing spoon. Life on Earth may owe its existence not just to the presence of water, but to the rhythmic patience of the moon drawing that water back and forth across the rocks of the young world. Let us now travel to the very threshold of what physics can describe, the Planck length, the smallest meaningful distance in the known universe. Named after the physicist Max Planck, this length is approximately 1.6 times 10 to the power of negative 35 meters, a number so small it is almost impossible to give it intuitive meaning. If an atom were scaled up to the size of the observable universe, the Planck length would be roughly the size of an actual atom within that scaled-up picture. Below the Planck length, our current theories of space and time, general relativity and quantum mechanics, both break down completely. They give nonsensical answers. They contradict each other in ways we do not yet know how to resolve. At the Planck scale, space and time themselves may not be continuous smooth surfaces, but something granular, foamy, or fundamentally discrete. A pixelated substrate from which the smooth space-time of our everyday experience somehow emerges. This is the frontier, the place where our two greatest theories of reality reach their limits and point towards something deeper that we have not yet found. The Planck length is not just a small number. It is the address of the universe's most profound unsolved mystery, the unification of quantum mechanics and gravity, a theory of everything that we are still searching for. Now, let us consider one of the most quietly astonishing aspects of the universe's long history, the concept of the galactic year and what it means for the age of our solar system in cosmic terms. The solar system orbits the center of the Milky Way at roughly 828,000 kilometers per hour, completing one full orbit approximately every 225 to 250 million years, a span of time called a cosmic year or galactic year. Our solar system is approximately 4.6 billion years old. In galactic years, that is roughly 18 to 20 orbits around the center of the Milky Way. When our solar system completed its first orbit, multicellular life had not yet appeared on Earth. When it completed its third orbit, the Great Permian extinction wiped out 90% of all species. When it completed its 17th orbit, the dinosaurs were still alive. And in the current orbit, the 20th, our species appeared, built cities, developed science, and sent spacecraft beyond the solar system. The Milky Way itself has been in existence for approximately 50 to 60 galactic years. When the galaxy was young and in its first orbits, there were no rocky planets anywhere within it. Not enough heavy elements had yet been forged. The conditions for worlds like Earth only became possible around the galaxy's 10th orbit. We live in a mature galaxy, in a solar system that arrived at just the right time in the galaxy's chemical history to inherit the elements needed for complexity, for chemistry, for life. As we drift in the deep quiet of this passage, let us reflect on one of the most intimate intersections between the cosmic and the everyday. The nuclear reactions that power not just the stars, but the warmth of the Earth beneath our feet. The interior of our planet is hot. Not merely warm, the core of the Earth reaches temperatures comparable to the surface of the Sun. Approximately 5,000 to 6,000 degrees Celsius. A significant portion of that heat comes from a source that surprises many people. The radioactive decay of elements like uranium, thorium, and potassium-40 distributed throughout the Earth's mantle and crust. These elements were forged in supernovae and in the collisions of neutron stars billions of years before our solar system formed. And they were incorporated into the young Earth during its accretion. Their nuclei have been slowly, spontaneously decaying ever since, releasing heat that drives the convection currents of the mantle, which in turn power plate tectonics, fuel volcanoes, and sustain the geodynamo that generates Earth's magnetic field. The magnetic field that shields us from the solar wind, that guardian of our atmosphere and our biology, is ultimately powered by the radioactive legacy of ancient stellar explosions. The warmth of the ground beneath you, the shield around the planet above you. Both are gifts from stars that died before the Earth was born. And here in our final reflection for this passage, let us consider the concept of look-back time and the extraordinary implication that the universe we observe is a kind of living museum, in which every direction we look reveals a different moment in cosmic history. When we observe a galaxy 1 billion light-years away, we are seeing it as it was 1 billion years ago. When we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. When our solar system did not yet exist. The night sky is not a flat backdrop. It is a four-dimensional landscape, receding not just in space, but in time, so that the further we look, the earlier the epoch we observe. This means that in a single night's observation, a telescope can capture galaxies at a dozen different stages of their evolution, young, irregular, star-forming galaxies in the distant background, mature spirals and ellipticals in the middle ground, our own mature cosmic neighborhood in the foreground. We do not need a time machine to see the past. We simply need to look up. The entire history of the universe is written in the light arriving at our eyes and instruments at this very moment, a cosmic archive that has been delivering its messages across billions of years, waiting patiently for a creature curious enough to read them. You are that creature. This is that moment. We breathe out slowly, and we let the universe hold everything we have carried tonight. The vast emptiness of cosmic voids, shaped by dark energy into the negative space of existence. The pale blue dot, home, suspended in a sunbeam, asking its quiet question. The shadows of distant moons falling across starlight, speaking in the language of geometry. The millisecond radio shouts from magnetars billions of light-years away. The moon stirring the tidal pools where life first assembled itself. The Planck length, the address of the deepest mystery. The 20 orbits our solar system has completed through the Milky Way. The radioactive warmth of ancient supernovae glowing in the ground beneath you. And the look-back time written in every direction of the night sky, the universe's entire history, arriving as light, ending in your awareness. You are not at the end of this story. You are in the middle of it, exactly where you are supposed to be, at exactly the right moment. Rest now. The stars will keep their vigil. And when you wake, the universe will still be here, older by a night and no less astonishing. We return once more. And there is something quietly remarkable about that, about the act of returning. Each time we come back to this journey, we arrive carrying everything that came before. The stardust and the deep time, the quantum tunnels and the tidal pools, the pale blue that's suspended in a sunbeam, the atoms older than the earth that form the substance of our hands and breath and wondering. We do not lose what we have gathered here. We carry it forward, the way the universe itself carries every moment of its past encoded in the structure of the present. We breathe, and we open, and we begin. Let us begin this passage with one of the most quietly staggering facts in the whole of planetary science, the discovery that it rains diamonds on Neptune and Uranus. The ice giant planets of our outer solar system are among the least understood worlds we have yet visited. Their interiors are thought to consist of a hot, dense mixture of water, ammonia, and methane compressed to pressures millions of times greater than Earth's surface. Under those extreme conditions, something extraordinary is predicted to occur. The carbon atoms in methane molecules are stripped free by the pressure and heat, and they are compressed so intensely that they crystallize, forming diamond. These diamond crystals are thought to sink through the planet's interior like rain through a thick atmosphere, drifting downward toward the core. Recent laboratory experiments have confirmed the process. Scientists recreated the interior pressures of Neptune using powerful lasers and observed diamond formation in real time. On Neptune, a world 8 times wider than Earth and nearly 4.5 billion kilometers from the Sun, it may be raining diamonds through an ocean of liquid carbon, settling into a vast diamond layer surrounding the planet's core. The solar system, even after decades of exploration, continues to exceed the most extravagant reaches of imagination. As we drift from the ice giants inward, let us consider one of the most transformative inventions in the history of human understanding, the telescope, and the revolution it has quietly sustained across 4 centuries. When Galileo Galilei first turned a spyglass toward the sky in 1609, he saw the moons of Jupiter moving around their planet, direct evidence that not everything in the cosmos revolved around the Earth. He saw the phases of Venus, the mountains of the moon, the countless stars of the Milky Way resolved from a soft glow into individual points of light. In that single act of looking, the architecture of the cosmos began to come into focus for the first time. Since then, each generation of telescope has revealed a deeper layer of reality. The spiral arms of galaxies, the expanding universe, the cosmic microwave background, gravitational lensing, black hole shadows, the atmospheres of distant exoplanets. The James Webb Space Telescope, now operating at the second Lagrange point 1.5 million kilometers from Earth, can detect the heat signature of a bumblebee at the distance of the moon. It peers back to within a few 100 million years of the Big Bang, gathering light from the universe's first galaxies. Every new telescope is a new set of eyes, and each pair of eyes reveals that the universe is larger, older, stranger, and more intricate than the last pair could see. We are always in astronomy at the beginning. Breathing gently, let us turn to a phenomenon that bridges the cosmic and the biological in one of the most surprising ways imaginable: the role of supernovae in shaping the evolution of life on Earth. We know that supernovae seed the galaxy with heavy elements, but their influence on life may extend to something far more direct. When a massive star explodes within a few hundred light years of our solar system, the shockwave and radiation it releases can compress nearby interstellar gas clouds, potentially triggering new star and planet formation. More remarkably, the cosmic rays produced in supernova shockwaves can penetrate Earth's atmosphere and reach the surface, influencing cloud formation patterns and potentially shifting climate. And there is evidence found in the geological record of elevated concentrations of iron-60, a radioactive isotope produced almost exclusively in supernovae, in ancient ocean sediment layers dating to approximately 2.5 million and 8 million years ago. These layers correspond to periods of significant ecological change in our own lineage's history. The possibility exists, still debated, but deeply fascinating, that nearby supernovae, by altering climate and opening ecological niches, may have played a role in the transitions that shaped our own evolutionary path. We may owe something of what we are not just to the distant supernovae that built our atoms, but to the nearer ones that helped sculpt the conditions in which our ancestors walked upright and grew curious. Let us now rest our attention on one of the most elegant and far-reaching ideas in all of physics, Noether's theorem, and the profound connection it reveals between symmetry and the laws of nature. In 1915, the mathematician Emmy Noether proved something that would quietly underpin all of modern physics: that every continuous symmetry in the laws of nature corresponds to a conserved quantity. If the laws of physics are the same today as they were yesterday, if they do not change with time, then energy must be conserved. If the laws of physics are the same here as they are a kilometer away, if they do not depend on position in space, then momentum must be conserved. If the laws are the same regardless of the direction you face, rotationally symmetric, then angular momentum must be conserved. The conservation laws that govern every interaction in the universe, the laws that keep planets in their orbits, that govern the behavior of every particle in every collision, are not arbitrary rules. They are the mathematical shadows cast by the symmetries of existence itself. Noether's theorem is one of the most beautiful results in all of human knowledge, a demonstration that the orderliness of the universe is not imposed from outside, but emerges inevitably from the structure of space and time. Order is not added to the universe, is woven into its fabric. As we float in quiet reflection, let us consider the extraordinary story of light pollution, and what we have lost, and what we stand to recover, in the battle between human brightness and the darkness of the ancient sky. For the vast majority of human history, every person who ever lived could step outside on a clear night and see the full sweep of the Milky Way overhead. Thousands of stars, the soft glow of our galaxy's core, the dark lanes of interstellar dust, perhaps the smudge of the Andromeda galaxy visible to the naked eye. This sky was not merely beautiful. It was the first library, the first calendar, the first map of time. It guided migrations, seeded mythologies, inspired the first astronomers. Today, approximately 1/3 of the human population, including 99% of people in the United States and Europe, can no longer see the Milky Way from where they live. The ancient sky has been erased by artificial light for the majority of humanity. And yet the universe has not gone anywhere. The stars are still there, burning with the same patient fire, waiting. In places far from city lights, the high deserts, the open oceans, the polar regions, the sky that our ancestors knew still exists in its full, overwhelming splendor. To stand beneath it is not merely a beautiful experience. It is a reunion with something that shaped the human mind across 100,000 years of evolution, a reminder that we belong to a sky far larger than the one most of us can currently see. Let us travel now to the surface of the Sun, or rather, just above it, and consider one of the most energetic and dangerous phenomena our star produces, a solar flare. Solar flares are sudden, intense bursts of radiation released when magnetic field lines in the Sun's atmosphere become twisted and stressed beyond their limit and snap into a new configuration, releasing an enormous amount of stored magnetic energy in a matter of minutes. The most powerful flares can release the equivalent of billions of nuclear weapons simultaneously, sending X-rays and ultraviolet radiation streaming across the solar system at the speed of light. On Earth, the X-rays from a strong solar flare arrive just 8 minutes after the eruption, causing immediate disruption to radio communications on the sunlit side of the planet. Larger eruptions can be accompanied by coronal mass ejections, the great plasma clouds we have touched on before, which arrive 1 to 3 days later, compressing Earth's magnetic field and driving geomagnetic storms. Astronauts in space, unprotected by Earth's atmosphere and magnetic field, can receive radiation doses from a major flare equivalent to thousands of chest X-rays. As we venture further from Earth, to the Moon, to Mars, to the asteroids, learning to forecast and shelter from solar flares will become one of the central challenges of human space exploration. Our star is generous with its light and warmth, but is also restless and powerful beyond anything we have yet tried to build. Breathing slowly, let us now consider the concept of stellar metallicity, and why the chemical richness of a star is one of the most important factors in determining whether it can host a planet like Earth. In astronomy, the term metal refers to every element heavier than hydrogen and helium, carbon, oxygen, silicon, iron, and all the rest. A star's metallicity is the proportion of these heavier elements in its composition, and it varies considerably across the galaxy and across cosmic time. Stars that formed early in the universe's history have very low metallicity. They were built almost entirely from the pristine hydrogen and helium of the Big Bang, with almost none of the heavier elements needed to form rocky planets, silicate minerals, or organic chemistry. As successive generations of stars lived and died, and enriched the interstellar medium with heavier elements, the metallicity of newly forming stars gradually increased. Our Sun sits comfortably in the upper range of metallicity for its age, meaning it formed from gas that had already been through multiple cycles of stellar processing. This is not incidental. It is the reason our solar system has 4 rocky inner planets. It is the reason Earth has a silicate mantle and an iron core. It is the reason carbon-based chemistry was available to build life. The richness of the universe's chemistry, and therefore the possibility of life, has been increasing slowly and steadily for 13.8 billion years. In a very real sense, the universe has been getting better at making worlds like ours. Now, let us journey inward, not into space, but into the strangeness of time once more, and consider a phenomenon that sits at one of the strangest intersections of general relativity and everyday life: gravitational time dilation, and the fact that your GPS navigation system only works because engineers accounted for Einstein's equations. Einstein's general theory of relativity predicts that time passes more slowly in stronger gravitational fields. A clock closer to the center of the Earth, deeper in its gravitational well, will tick fractionally more slowly than one at higher altitude. The GPS satellites orbiting Earth at approximately 20,000 kilometers altitude experience weaker gravity than clocks on the surface, and therefore their onboard atomic clocks run slightly faster, gaining approximately 45 microseconds per day relative to clocks on the ground. There is also a smaller competing effect from special relativity. Because the satellites are moving quickly in orbit, their clocks run slightly slower, losing about 7 microseconds per day. The net result is that GPS satellite clocks gain roughly 38 microseconds per day relative to ground-based clocks. This sounds trivial, but GPS navigation works by timing signals to nanosecond precision. An uncorrected error of 38 microseconds per day would cause GPS position errors to accumulate at a rate of about 10 kilometers per day, making the entire system useless within hours. Every time you navigate by GPS, your device is silently applying Einstein's equations to compensate for the curvature of space-time around our planet. General relativity is not an abstract theory. It is running in the background of everyday life. And here, in our final reflection for this passage, let us sit with one of the most humbling and liberating ideas the universe offers us, the concept of cosmic perspective, and what it genuinely means to hold it, not just intellectually, but as a lived feeling. We speak often in our culture about feeling small in the face of the universe. But the great astronomers and physicists who have spent their lives staring into the cosmos report something rather different. They report not smallness, but connection. Not insignificance, but membership. The universe did not make us accidentally and abandon us. It spent 13.8 billion years building the conditions that would allow atoms to arrange themselves into something that could wonder about its own existence. The carbon in your body was fused in a star. The iron in your blood was forged in a supernova. The water in your cells was assembled in interstellar clouds and delivered by comets. You are not a stranger to the cosmos, looking in through a window. You are the cosmos, looking at itself through the extraordinary instrument of a conscious mind. And whatever difficulties the day has held, whatever weight you carry into this night, you are also, at the same time, an ancient thing. A patient thing, built from stardust and deep time, held together by the same forces that hold galaxies together, temporary in form, but continuous in substance with everything that has ever existed or will ever exist. That is not a small thing to be. That may be the largest thing there is. We breathe out long and slow, and we let it all come to rest. Diamond rain falling through the hearts of ice giants. For centuries of telescopes opening humanity's eyes, one generation at a time. Supernovae that may have nudged our ancestors toward becoming human. The symmetries of existence giving rise to all the conservation laws of nature. The ancient sky, still waiting beyond the glow of our cities, unchanged and patient. The restless surface of our generous star. The galaxy slowly enriching itself across deep time, growing more capable of making worlds like ours. Einstein's equations quietly bending time inside every GPS satellite above us right now. And the largest truth of all, that you are not small in this universe. You are made of it, sustained by it, continuous with it, in ways that no distance and no darkness can undo. Rest here. You are home. You have always been home. And the story, extraordinary, unfinished, and endlessly generous, goes on. We return, as we always return, not because we have not yet arrived, but because arriving is the journey. Each passage through these cosmic depths changes something in the way we hold ourselves. We become, slowly, a little more at home in the vastness, a little less afraid of the scale, a little more willing to accept that mystery is not the absence of meaning, but perhaps its deepest form. The universe has been here for 13.8 billion years, and it has never once hurried. Neither shall we. We breathe and we begin. Let us open this passage with one of the most ancient and beautiful instruments of human timekeeping, and the extraordinary cosmic mechanics that make it work. The calendar we use today, the rhythm of our days and seasons and years, is ultimately a record of Earth's relationship with the sun and moon. A relationship written in orbital mechanics and gravitational physics, stretching back to the formation of the solar system. The length of our year, 365.25 days, is the time it takes Earth to complete one orbit around the sun. The length of our month traces its origin to the moon's orbital period. The length of our day is Earth's rotational period. But here is what makes this profound. These periods are not fixed forever. The moon is slowly drifting away from Earth, moving outward by approximately 3.8 centimeters per year as tidal forces transfer angular momentum from Earth's rotation to the moon's orbit. As a result, Earth's rotation is very gradually slowing. A day on Earth 1.4 billion years ago lasted only about 18 hours. The moon was closer, the tides were larger, and the planets spun faster beneath them. A billion years from now, a day will be longer still. The calendar is not a human invention imposed on a static universe. It is a snapshot of a gravitational conversation between our world and its companions, a conversation that has been slowly, continuously evolving since the solar system was born. As we drift gently onward, let us consider one of the strangest predictions of modern cosmology, the existence of cosmic strings. These are not strings in the musical sense, nor in the metaphorical one, but hypothetical one-dimensional defects in the fabric of space-time itself, relics of phase transitions that may have occurred in the very early universe. Fractions of a second after the Big Bang, as the cosmos cooled and the unified forces of nature separated into the distinct forces we know today. If cosmic strings exist, they would be unimaginably thin, far narrower than a proton, yet contain the mass energy equivalent of millions of suns packed into every kilometer of their length. A single loop of cosmic string passing through a galaxy could cause gravitational lensing effects, splitting background light sources into double images as it moved. Networks of oscillating cosmic strings would produce a background of gravitational waves with a characteristic signature that current and future gravitational wave observatories may be able to detect. Cosmic strings have not yet been confirmed, but they have also not been ruled out. They sit at the frontier between what physics predicts and what observation has yet to find. One of a family of exotic structures that remind us that the very early universe may have left behind relics stranger than anything we have directly observed, still moving through the cosmos today, waiting to be found. Breathing slowly, let us turn to a story of scientific courage and the power of an unexpected observation, the discovery of the cosmic microwave background and what it meant for our understanding of the universe's origin. In 1964, two radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were attempting to use a large horn-shaped antenna to make precise measurements of radio signals from the Milky Way. No matter how carefully they calibrated their instrument, no matter what direction they pointed it, they detected a persistent, uniform hiss of microwave radiation coming equally from all directions in the sky. They cleaned pigeon droppings from the antenna. They checked every component for faults. The hiss remained. What Penzias and Wilson had stumbled upon, and for which they would later receive the Nobel Prize, was the cosmic microwave background. The faint afterglow of the Big Bang itself, the oldest light in the universe, stretched by 13.8 billion years of cosmic expansion from the brilliant fireball of recombination into the microwave frequencies detectable today. is perhaps the most accidental great discovery in the history of science. Two engineers trying to eliminate noise from an antenna, inadvertently hearing the echo of creation. The universe announced its own birth to a pair of scientists who were not, at that moment, looking for it. It simply would not be ignored. Let us now consider something that lives at the intersection of physics and philosophy, the anthropic principle, and the profound question of why the universe seems suited to our existence. We have spoken in earlier passages of the fine-tuning of the universe's fundamental constants. The strength of gravity, the mass of the electron, the energy of the vacuum. Change any of these even slightly, and stars cannot form, atoms cannot exist, life as we know it becomes impossible. The anthropic principle offers one response to this puzzle. In its most modest form, it simply notes that we should not be surprised to find ourselves in a universe compatible with our existence, because if it were not compatible, we would not be here to observe it. A universe without stars, without atoms, without the long cosmic history needed to produce chemistry and biology, would be a universe without observers. The very act of asking the question selects for a universe that permits the question to be asked. This is not quite an answer to why the constants have the values they do. It is more a reminder that our existence is itself a form of evidence about the kind of universe we inhabit. Whether this reflects a vast multiverse of varying constants, or a deeper law we have not yet discovered, or something beyond current physics entirely, it leaves us with a universe that looks, from the inside, as though it was made with us in mind, even if the truth is that we were made by it. As we rest in that gentle wonder, let us travel to one of the most extreme environments in the solar system, the surface of Venus, Earth's nearest planetary neighbor, and in many ways, its most cautionary twin. Venus is almost exactly the same size as Earth, formed at roughly the same time, from roughly the same materials, and not dramatically different distance from the Sun. And yet Venus today is a hellscape. Its surface temperature averages around 465 degrees Celsius, hot enough to melt lead, maintained by a crushing atmosphere of carbon dioxide 90 times denser than Earth's, producing a runaway greenhouse effect of extraordinary intensity. The atmospheric pressure at the surface of Venus is equivalent to being 900 meters underwater on Earth. Clouds of sulfuric acid drift through the upper atmosphere. The longest any spacecraft has survived on the Venusian surface is just over 2 hours. How did two such similar worlds arrive at such different fates? The answer appears to lie in the early loss of Venus's water. Without oceans, the carbon cycle that regulates Earth's temperature, drawing CO2 out of the atmosphere through weathering, never established itself on Venus. Without a moderating mechanism, the greenhouse effect escalated over billions of years to its current extreme. Venus is a mirror held up to Earth, a reminder that habitability is not guaranteed by size or position alone. That the balance of conditions that keeps a planet livable is far more fragile than it might appear from the inside. Let us now breathe and consider one of the most intimate and surprising connections between the cosmos and the human body. The fact that the ratio of elements in your blood plasma is remarkably similar to the ratio of elements in seawater. The early oceans of Earth, in which life first emerged and in which it evolved for billions of years before venturing onto land, contained dissolved minerals in proportions that became, over deep evolutionary time, the internal chemistry of every living cell. When the ancestors of land animals first crawled from the sea, they carried the sea with them, locked inside the fluid that bathes every cell in their bodies. Your blood plasma contains sodium, potassium, calcium, and magnesium in concentrations that echo, imperfectly but unmistakably, the mineral composition of the ancient ocean. You are, in a very literal chemical sense, still partly an ocean creature, carrying your ancestral water inside you. And those minerals in the sea, the sodium, the magnesium, the calcium, were themselves forged in stellar interiors and scattered across space by supernovae before being gathered into the young Earth and dissolved into its oceans. The salt in your blood has been on a journey from the heart of a dying star to the ocean of the young Earth, to the interior of the first living cells to you. That is not a metaphor. That is chemistry. Drifting onward, let us consider the phenomenon of gravitational waves in a new light. Not their detection, which we have visited before, but what they reveal about the universe's most violent and creative events. The merger of neutron stars and the extraordinary fact that these collisions are one of the universe's primary forges of gold. When two neutron stars spiral together and collide, the energies involved are so extreme that protons and neutrons are forced together in ways that can only occur in such cataclysmic conditions, synthesizing heavy elements in a process called rapid neutron capture, or the R process. In a fraction of a second, a merging neutron star pair can produce quantities of gold, platinum, uranium, and other heavy elements equivalent to several times the mass of the Earth. In August 2017, astronomers detected both gravitational waves and a burst of light from a neutron-star merger 130 million light-years away. The first time such an event had been observed across multiple channels simultaneously. The light signal confirmed the production of heavy elements in the merger, including gold. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a reactor. All of it was produced, overwhelmingly, in the violent embrace of dying neutron stars. The most precious materials in human civilization are the debris of the cosmos's most violent collisions. Now, let us consider one of the most mind-expanding realizations in the history of science, the discovery that the universe had a beginning, and what that implies about the nature of time itself. For most of human history, and even for many scientists well into the 20th century, the prevailing assumption was that the universe had always existed, that it was eternal, static, and infinite. The steady-state model, championed by Fred Hoyle and others into the 1960s, held that new matter was continuously created to fill the gaps left by expansion, maintaining an eternal, unchanging cosmic landscape. The discovery of the cosmic microwave background in 1964, combined with the evidence for cosmic expansion already seen by Hubble, demolished this picture. The universe had a beginning. There was a moment, approximately 13.8 billion years ago, before which the universe, as we know it, did not exist, and after which everything that has ever happened followed in an unbroken chain of cause and consequence down to this present moment. The implications are staggering. Every event in history, every life ever lived, every thought ever thought, is part of a sequence that traces back, without interruption, to the first fraction of a second of existence. There is an unbroken thread connecting the Big Bang to the breath you are drawing right now. Nothing has been lost along the way. Everything that has ever happened is encoded, in some form, in the state of the universe today. The present is the total and complete consequence of everything that has ever occurred. And the future, open, unwritten, full of possibility, is waiting to be made. We breathe out long and unhurried, and we let it all settle into the body like warmth after a long walk in cold air. The slowing spin of our world, the lengthening day, the moon drifting outward by the width of a hand each year. The hypothetical cosmic strings threading the universe like ancient scars from its first moments. The accidental Nobel Prize, two engineers cleaning pigeon droppings from an antenna, hearing the echo of creation. The anthropic principle holding its quiet mirror up to existence. The hellish twin of our world, reminding us how lucky the balance of our living planet truly is. The ancient ocean chemistry that lives on in the salt of your blood. The gold in a wedding ring forged in the collision of two dying stars. And the unbroken thread, 13.8 billion years long without a single gap, connecting the first moment of everything to the breath you are breathing right now. You are not separate from that thread. You are it expressing itself at this particular place and time, aware and wondering and alive. Rest in that knowing. It is enough. It has always been enough. We return once more to the quiet at the center of everything. By now, these passages have become something like a practice, a regular turning of the attention toward what is vast and ancient and true. A deliberate setting down of the smaller weights we carry, a remembering of the larger story we belong to. The universe has not changed since we last met. But perhaps we have, in the way that any sustained encounter with something beautiful and true changes us, gradually, without our quite noticing, until one day we look up and find the world a little wider than it was. We breathe and we continue. Let us begin this passage with one of the most haunting and scientifically rich mysteries in the history of radio astronomy, the WOW signal. On the night of August 15, 1977, a radio telescope at Ohio State University called Big Ear was scanning the sky as part of the search for extraterrestrial intelligence, SETI, project. The telescope was automated, and the data was printed on paper for later review. When astronomer Jerry Emmon examined the printouts several days later, he found a sequence of characters so startlingly strong, so precisely matching what a signal of extraterrestrial intelligent origin might look like, a narrowband transmission near the hydrogen line frequency. The wavelength most likely to be chosen by any technologically sophisticated civilization as a universal cosmic reading, that he circled it in red pen and wrote a single word in the margin. Wow! The signal lasted 72 seconds, precisely the duration expected for a signal from a fixed point in the sky, as Earth rotated beneath it. It has never been detected again, despite decades of follow-up observations pointed at the same region of sky. Its origin remains officially unexplained. It may have been a natural phenomenon, a satellite reflection, a statistical fluke. Or it may have been something else entirely. The WOW signal does not prove that we are not alone, but it has never quite let us forget the question. As we float gently from that open question, let us consider one of the most elegant demonstrations of the universe's deep mathematical structure, the Fibonacci sequence, and the way it emerges not from human design, but from the physics of growth itself. The Fibonacci sequence, in which each number is the sum of the two preceding ones, 1, 1, 2, 3, 5, 8, 13, 21, and so on, appears with remarkable frequency in the biological world. The spirals of a nautilus shell, the arrangement of seeds in a sunflower, the branching of a tree, the arrangement of leaves around a stem, the pattern of scales on a pine cone, all of these follow Fibonacci proportions. This is not coincidence or mysticism. It is physics. When a growing organism adds new material at its edge, a new leaf, a new seed, a new chamber, the most efficient packing, the configuration that maximizes exposure to sunlight or minimizes wasted space, turns out to correspond to the golden angle, approximately 137.5 degrees. And the golden angle is mathematically derived from the golden ratio, which is the limit of successive Fibonacci number ratios as the sequence extends. Life, growing outward from a center, finds Fibonacci spirals not because it has been told to, but because that is what efficient self-similar growth looks like when governed by consistent physical rules. The mathematics of the universe and the mathematics of life are not two different things. They are the same thing, expressed at different scales. Breathing softly, let us now consider one of the most extraordinary missions in the history of space exploration, the New Horizons flyby of Pluto, and what it revealed about the extraordinary richness of the outer solar system. For decades after its discovery in 1930, Pluto was thought to be a small, featureless, frozen rock at the edge of the solar system, a dim, static relic. When New Horizons arrived in July 2015, after a journey of 9.5 years and nearly 5 billion kilometers, the images it returned sent shock through the planetary science community. Pluto's surface is geologically active. It hosts towering mountains of water ice as tall as the Rockies, floating on a substrate of nitrogen ice that slowly convects like a very cold lava lamp. It has a vast heart-shaped plain, informally named Tombaugh Regio, made of nitrogen and carbon monoxide ice, so reflective it blazes white against the surrounding terrain. It has a thin but complex atmosphere of nitrogen and methane that rises and falls seasonally as Pluto's elliptical orbit carries it closer to and farther from the Sun. And in 2019, New Horizons flew past an even more distant object, Arrokoth, a contact binary Kuiper Belt object shaped like a reddish snowman, whose two lobes gently merged billions of years ago in the softest collision in solar system history. The outer reaches of our solar system are not dead and empty. They are ancient, preserved, and full of surprises. Let us now turn to a concept that reaches into the heart of what it means for something to be real. The many worlds interpretation of quantum mechanics proposed by physicist Hugh Everett III in 1957. Quantum mechanics tells us that before a quantum event is observed or measured, a particle exists in a superposition of all its possible states simultaneously. The standard interpretation, called the Copenhagen interpretation, says that the act of measurement causes this superposition to collapse into a single definite outcome. Everett proposed a different view, that the wave function never collapses at all. Instead, at every quantum event, the universe branches, every possible outcome occurs in a separate, equally real branch of reality. In one branch, the particle went left. In another, it went right. Both outcomes are real. Both branches continue to evolve, diverging further with every subsequent quantum event. Under many worlds, the universe is constantly and silently branching into an unimaginably vast tree of parallel realities. Each one as real as this one, each inhabited by versions of every particle, every atom, every person. We cannot communicate with these other branches. We cannot detect them. But the mathematics of quantum mechanics, in Everett's reading, does not merely allow them, it demands them. Many worlds remains controversial and passionately debated. But it is taken seriously by a significant number of physicists because it solves with elegant simplicity the deepest paradox in quantum theory. Not by adding anything to the mathematics, but by taking it completely literally. As we breathe and settle deeper, let us consider something that lives entirely in the present tense, the extraordinary precision of atomic clocks and what they reveal about the nature of time. An atomic clock works by tuning into the precise frequency at which atoms of a specific element, typically cesium-133, oscillate between two energy states. The cesium atom oscillates at exactly 9,192,631,770 cycles per second, a frequency so stable and so reproducible that it has been adopted as the international definition of the second itself. The most advanced atomic clocks currently in operation are so precise that they would neither gain nor lose a single second in approximately 300 million years. This extraordinary precision has applications far beyond mere timekeeping. It enables GPS navigation, as we have seen. It allows scientists to test general relativity at previously impossible levels of precision, detecting the fractional time dilation between clocks separated by just a few centimeters of altitude. It may eventually allow us to detect the gravitational waves produced by intermediate mass black hole mergers, or to map variations in Earth's gravitational field with enough sensitivity to monitor groundwater levels and magma movement beneath volcanoes. The atom, vibrating faithfully at the same frequency it has vibrated at since matter first formed in the early universe, has become humanity's most precise ruler of time, a cosmic metronome, ticking in the same rhythm whether it sits in a laboratory on Earth or drifts somewhere in the space between galaxies. Let us now drift towards something that has shaped civilizations, inspire mythologies, and continues to stir something ancient and navigational in the human spirit: the North Star, Polaris, and the slow celestial phenomenon behind it. Polaris sits almost directly above Earth's North Pole, appearing nearly motionless in the sky, while all other stars appear to circle around it over the course of a night. For this reason it has been used for navigation across cultures and centuries. But Polaris was not always the pole star and will not always be. Earth's rotational axis is not fixed in space. It wobbles slowly like a spinning top that is not quite vertical, tracing a slow circle in the sky over a period of approximately 26,000 years, a process called axial precession. At the time the ancient Egyptians built the pyramids, the pole star was not Polaris but Thuban, a star in the constellation Draco. In approximately 12,000 years, the brilliant star Vega, one of the brightest in our sky, will take its turn as the northern pole star. The night sky itself is in slow, stately motion, the constellations shifting their relationships to the celestial poles across timescales of thousands of years. The sky that guided the first sailors is not quite the same sky that guided them, and the sky our distant descendants will see will be different again. The cosmos does not hold still for anyone. It is always changing, always in motion, always becoming something slightly new. Breathing gently, let us consider the remarkable phenomenon of panspermia, the hypothesis that life, or the chemical precursors to life, may travel between worlds aboard comets and asteroids, spreading through the galaxy over vast timescales. We know that material can be transferred between planets. Meteorites on Earth have been identified as fragments of Mars, blasted free by ancient asteroid impacts and eventually captured by Earth's gravity after long journeys through the inner solar system. We know that simple organisms, bacterial spores, tardigrades, certain fungi, can survive the vacuum of space and intense radiation for extended periods. We know that amino acids and other organic molecules have been found aboard meteorites, having survived the journey through space and the heat of atmospheric entry. Panspermia does not require that life is transported intact between stars, though a more speculative version called lithopanspermia suggests even that may be possible on very long timescales. More modestly, it suggests that the chemistry of life, the building blocks, the molecular templates, the organic scaffolding, may be spread broadly through a solar system and perhaps between neighboring systems over billions of years. If panspermia operates even partially, it means life is not something that must arise independently on each world from scratch. It means the seeds of life may be ancient wanderers, scattered by the violence of impacts and the patience of gravity across the solar neighborhood, looking for worlds where they might, at last, take root. And here, in our final reflection for this passage, let us sit with the concept of entropy one more time, but from a different angle, one that transforms it from a story of decay into something unexpectedly generous. We have spoken of entropy as the universe's tendency toward disorder, as the arrow of time, as the engine running toward the eventual heat-death of everything. All of that is true, but there is another way to hold it. In the 19th century, the physicist Ludwig Boltzmann showed that entropy is not merely disorder in some vague sense, it is a precise measure of the number of ways a system can be arranged. A high-entropy state has many possible arrangements. A low-entropy state has very few. And the extraordinary thing, the thing that makes life, complexity, and consciousness possible, is that the universe began in a state of vanishingly low entropy. A near-perfect uniformity, a near-perfect simplicity, a near-perfect order. Out of that initial order, entropy has been increasing ever since. And as it increases, as energy flows from concentrated to dispersed, it does not merely create disorder. It creates gradients. And gradients drive processes. Waterfalls, winds, ocean currents, metabolic reactions, neural activity, thought, all of these are entropy in action. Every moment of beauty, every act of love, every human achievement, every star blazing against the night, all of it is the universe spending its initial endowment of low entropy, converting order into experience. We are not witnessing the universe running down. We are riding the wave of its unfolding, a wave that began at the moment of creation, and that carries us and everything we have ever known in its long, luminous, irreversible forward motion. We breathe out all the way, and we let the universe hold everything we have brought here tonight. The 72-second signal from a fixed point in the sky, circled in red pen by a man who dared to wonder. The Fibonacci spirals of a sunflower, the mathematics of life, and the mathematics of the cosmos speaking in the same voice. The mountains of water ice on Pluto, floating on a slowly churning nitrogen sea, 9 years and 5 billion kilometers from home. The branching tree of many worlds, each quantum event a quiet parting of realities. The cesium atom, vibrating at its ancient frequency, keeping the most precise time in human history. The slow wobble of Earth's axis, moving the pole star across the sky, across thousands of years of human civilization. The seeds of life, perhaps drifting between worlds on ancient stone. And entropy, not as ending but as engine, the wave on which all experience rides from the first moment of creation to this breath, to this moment of rest, to whatever extraordinary thing comes next. You are the universe, breathing. Sleep well. We will travel on. We return, as we have returned so many times now, to the stillness at the center of the story. There is a kind of trust that grows from returning to the same practice over time. A deepening familiarity, a sense that the vast and the ancient are not remote from us, but woven into us, present in the act of breathing, present in the warmth of the body, present in the quiet hum of existence that underlies even the busiest and most difficult of days. The universe does not ask us to understand it all at once. It asks only that we keep returning. And so we do. We breathe and we begin. Let us open this passage with one of the most visually spectacular and scientifically extraordinary events the cosmos offers us here on Earth, a total solar eclipse. The precise geometry required for a total eclipse is almost absurdly improbable. The Sun is approximately 400 times wider than the Moon, and the Sun is approximately 400 times farther away. These two coincidences, one of size, one of distance, mean that from Earth's surface, the Sun and the Moon appear almost exactly the same size in the sky. During a total eclipse, the Moon covers the solar disk with a precision that reveals, and only reveals in that moment of perfect alignment, the Sun's outer corona. The ghostly, pearlescent atmosphere that extends millions of kilometers into space but is normally invisible against the blazing solar surface. This precise match is not a permanent feature of our solar system. The Moon is slowly drifting away from Earth, as we have discussed. In approximately 600 million years, the Moon will be too far away to completely cover the Sun, and total solar eclipses will no longer be possible. We live in a narrow window of cosmic time, a few 100 million years wide, during which total solar eclipses are possible on Earth. The fact that we exist within that window and have developed eyes and curiosity and science precisely during the epoch when the sky offers this particular wonder is one of the more quietly extraordinary coincidences in the history of our species. Drifting gently onward, let us consider the extraordinary depth of information locked inside ice, and what the planet's glaciers and ice sheets have preserved for science to read. When snow falls and compresses into glacier ice over hundreds and thousands of years, it traps tiny bubbles of the atmosphere that existed at the time of snowfall. These bubbles are time capsules, sealed samples of ancient air, preserved intact for hundreds of thousands of years deep in the ice of Antarctica and Greenland. By drilling ice cores, cylinders of ice extracted from depths of up to 3 kilometers, scientists can extract these bubbles and analyze their chemistry directly, measuring the concentrations of carbon dioxide, methane, and other gases in Earth's atmosphere going back as far as 800,000 years. The record they contain is extraordinarily detailed. It shows the rhythmic cycling of ice ages and interglacials driven by subtle variations in Earth's orbit called Milankovitch cycles. It shows the tight coupling between atmospheric greenhouse gas concentrations and global temperature across deep time. And it shows, with stark clarity in its most recent layers, the abrupt and dramatic increase in carbon dioxide that has occurred since the Industrial Revolution, a change with no parallel in the entire 800,000-year record. The ice is not merely frozen water. It is the planet's diary, written in ancient air, waiting patiently in the cold for someone to learn to read it. As we breathe and settle, let us consider one of the most consequential and least celebrated revolutions in the history of human thought, the Copernican revolution, and the principle it established that continues to guide science today. In 1543, Nicholas Copernicus proposed that the Earth was not the center of the universe, but merely one of several planets orbiting the Sun. This was not simply an astronomical adjustment. It was a philosophical earthquake. For millennia, the assumption had been that humanity occupied a special, central position in the cosmos. Copernicus displaced us from that center. Galileo confirmed it with a telescope. Subsequent centuries showed that the Sun itself is not central. It is one ordinary star among hundreds of billions in an ordinary galaxy, itself one of trillions. The principle that emerged from this series of displacements is called the Copernican principle, or sometimes the principle of mediocrity. The idea that we should not assume without strong evidence that our position or our moment or our world is special among all positions, moments, and worlds. And yet here is the beautiful tension at the heart of this principle. While our position may not be cosmically central, our existence demonstrably is extraordinary. The universe is vast and mostly empty and mostly dark. Complexity, chemistry, life, and consciousness are vanishingly rare in terms of the volume of space they occupy. The Copernican principle keeps us humble about our location. It does not and cannot make us ordinary in any other sense. Let us now turn our attention to one of the most technically ambitious and scientifically revelatory missions in the history of planetary exploration, the Cassini spacecraft's 17 years in the Saturn system. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years in orbit around the ring giant, returning over 450,000 images and a staggering volume of scientific data that transformed our understanding of the Saturn system and the solar system as a whole. It revealed the dynamics of Saturn's rings in extraordinary detail, the waves and gaps carved by gravitational resonances with moons, the translucent inner rings through which the planet's shadow falls like light through lace. It watched seasonal changes unfold in Saturn's atmosphere across years, documented the hexagonal polar storm, a persistent six-sided vortex at Saturn's north pole that has no clear analog anywhere else in the solar system, and plunged through the geysers of Enceladus to taste the chemistry of its subsurface ocean. In September 2017, when Cassini's fuel was finally exhausted, mission controllers deliberately plunged it into Saturn's atmosphere, both to prevent contamination of the potentially life-bearing moons and to gather atmospheric data during its final descent. It became part of the planet it had spent 13 years studying. There is something quietly profound about that ending. A machine built by human hands, traveling billions of kilometers from home, becoming, at last, a part of Saturn. Breathing slowly, let us consider one of the strangest and most disorienting facts in modern cosmology, the concept of inflation, and what it implies about the regions of the universe we will never see. In the first fraction of a second after the Big Bang, somewhere between 10 to the power of negative 36 and 10 to the power of negative 32 seconds, the universe is thought to have undergone a period of exponential expansion called cosmic inflation, during which space expanded by a factor of at least 10 to the power of 26, and possibly vastly more, in almost inconceivably short time. This expansion was so rapid that regions of space which had been in causal contact, close enough to exchange information or energy, were suddenly separated by distances far greater than light could ever bridge, even given the entire age of the universe to travel. What this means is that the observable universe, the sphere of space from which light has had time to reach us in 13.8 billion years, is not the whole universe, is a tiny bubble within a vastly larger whole. Beyond the edge of our observable horizon, the universe continues, and if inflation proceeded long enough, it continues for distances so incomprehensibly large that the observable universe, with its 2 trillion galaxies, would be to the full universe as a single atom is to the observable universe itself. We cannot see beyond our horizon. We cannot send a signal there. But the universe out there is just as real, just as full, and just as ancient as the one we can see. Our entire cosmic history is a footnote on a footnote. Let us now consider the beautiful and vertiginous phenomenon of stellar parallax, the method by which we first measured the true distances to the nearest stars, and in doing so, grasp for the first time the staggering true scale of the universe beyond our solar system. Hold a finger up in front of your face and close one eye, then the other. Your finger appears to shift against the background. This is parallax, the apparent change in position of a nearby object against a distant background when viewed from different positions. Astronomers use the same principle on a vastly larger scale. As Earth orbits the Sun, our position in space shifts by up to 300 million kilometers over the course of 6 months. Nearby stars, viewed against the backdrop of much more distant ones, appear to shift very slightly in position between observations made 6 months apart. The first successful measurement of stellar parallax was made in 1838 by Friedrich Bessel for the star 61 Cygni. The shift he measured was less than a third of a second of arc, a tiny fraction of 1 degree, yet it told him that 61 Cygni was approximately 10 light-years away. That measurement, that almost impossibly small angular shift, was the moment humanity first truly understood the scale of the stellar universe. The nearest stars were not close. They were unimaginably, incomprehensibly far. And the galaxy beyond them was further still. The universe did not shrink in that moment. Our understanding of our own smallness within it grew, irreversibly, into something closer to the truth. As we drift in quiet wonder, let us consider the phenomenon of chemical evolution. The universe's long journey from the simplicity of hydrogen and helium toward the extraordinary molecular complexity that eventually gave rise to life. In the minutes after the Big Bang, only the lightest elements existed. The first stars converted hydrogen and helium into carbon, oxygen, nitrogen, and neon. Supernovae and neutron star mergers added the heavier elements: iron, silicon, sulfur, gold, uranium. Over billions of years and multiple generations of stars, the interstellar medium grew steadily richer in chemical complexity. In the cold molecular clouds where new stars form, atoms combined into molecules: water, carbon monoxide, ammonia, formaldehyde, and more than 200 others detected so far. On the surfaces of dust grains, shielded from radiation, more complex organic molecules assembled slowly in the dark. Comets and asteroids carried this chemistry into young solar systems. On worlds with liquid water and energy gradients, chemistry crossed the threshold into biochemistry: self-replicating molecules, membranes, metabolism. Life was not a departure from chemistry. It was chemistry's continuation by other means, the universe finding new and increasingly intricate ways to process energy, store information, and respond to its environment. We are not exceptions to the laws of chemistry. We are their most complex known expression, the universe's chemistry temporarily arranged into something that can look back at itself and wonder how it got here. And here, as we draw toward the close of this passage, let us sit with one of the most quietly radical and personally transformative ideas that cosmology offers, the idea of cosmic impermanence, and the peace that comes from truly accepting it. Nothing in the universe lasts forever. Stars burn out. Galaxies collide and dissolve. Black holes slowly evaporate across unimaginable timescales. The very protons that make up ordinary matter may, according to some theories, eventually decay over timescales of 10 to the power of 34 years or more. Impermanence is not a flaw in the design of the universe, is the design. And in every tradition of human wisdom, from the Buddhist recognition of anicca, the transience of all things, to the Stoic reflection on mortality as a teacher of presence, the acceptance of impermanence has been understood not as a cause for despair, but as an invitation to a deeper and more attentive way of living. The fact that a star will one day exhaust its fuel does not diminish the billion years of light it offers. The fact that a human life is brief against the backdrop of cosmic time does not make it less real, less felt, less meaningful. If anything, impermanence is what gives experience its texture and its weight. A universe in which nothing ever ended would be a universe in which nothing was ever fully itself. The brevity of things is what makes them what they are. And the willingness to hold that truth, to rest in it rather than resist it, may be one of the deepest forms of wisdom the cosmos has to teach us. We breathe out, slowly and completely, and we rest in everything this journey has brought us to. The fleeting geometric miracle of a total solar eclipse, possible only in this brief window of cosmic time. The ancient air sealed in glacier ice, the planet's own diary written in bubbles. The Copernican humility that keeps us honest, and the extraordinary rarity of complexity that keeps us grateful. Cassini becoming Saturn. The unimaginable vastness beyond our cosmic horizon, where the observable universe is a footnote on a footnote. The tiny angular shift that first revealed the true scale of the stellar universe. The long chemical evolution from hydrogen to heartbeat. And the quiet, liberating truth of impermanence, that the brevity of things is not their tragedy, but the very quality that makes them real. You are brief. You are rare. You are made of ancient things and held by forces that have governed matter since the first moment of existence. And in this moment, in this breath, you are exactly what the universe has been slowly, patiently, magnificently becoming. Rest here. You have earned it, and the stars, as always, will keep watch. We return. We always return. And in the returning there is something the universe itself seems to model for us. The way it cycles, the way it folds back on itself across every scale, the way a river delta and a nerve cell and a bolt of lightning and the branching of the cosmic web all trace the same patient logic of flow, finding its way through resistance. We are part of that flow. We have been since the first moment. And in these passages together, we have been practicing the art of remembering it, of letting the weight of the ordinary temporarily lift, and feeling for a little while what it is like to be an ancient thing in an ancient universe, curious and awake and grateful. We breathe and we begin. Let us open this passage with one of the most astonishing recent discoveries in planetary science. The detection of organic molecules and phosphorus in the plumes of Enceladus by the Cassini spacecraft, and what it may mean for the question of life beyond Earth. We have spoken before of Enceladus and its subsurface ocean. But in the years since Cassini's plume flybys, the data it collected has continued to yield revelations. In 2023, scientists analyzing Cassini's archived data announced the detection of phosphorus compounds in the plume material, making Enceladus the first world beyond Earth confirmed to contain all 6 of the chemical elements considered essential for life as we know it: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the elements from which DNA, proteins, cell membranes, and the entire molecular machinery of biology are built. Enceladus's ocean is not merely wet. It is chemically rich in precisely the ways that matter most for life. The ocean floor of Enceladus, where hydrothermal vents are thought to exhale warm mineral-rich water into the dark, may represent one of the most promising environments for life in the entire solar system, more accessible in some ways than Mars, because the chemistry is actively venting itself into space, where a passing spacecraft can taste it. The universe may not be making us wait long to find out whether we are alone. Drifting gently from that warm, dark ocean, let us consider one of the most elegant and far-reaching ideas in all of theoretical physics, the concept of symmetry breaking, and how the very structure of the physical world as we know it emerged from a universe that was, at its very beginning, simpler and more uniform than anything we can directly observe. In the first fractions of a second after the Big Bang, the universe was so hot and dense that the forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are thought to have been unified into a single force, indistinguishable from one another. As the universe expanded and cooled, it underwent a series of phase transitions, moments when the perfect symmetry of that unified state broke, and the distinct forces separated out, like water freezing into ice crystals whose symmetry is lower than the liquid from which they formed. With each symmetry breaking, the universe became more complex, more structured, more differentiated. The laws of physics we observe today, with their distinct forces, their specific particle masses, their particular constants, are not the most fundamental laws of the universe. They are the result of a series of symmetry breakings that occurred in the universe's first moments, each one adding structure and distinction to what had been smooth and unified. The richness of the physical world, all of its diversity, all of its complexity, is the consequence of a universe that was once too simple to contain any of it, cooling into structure the way a clear liquid cools into an intricate crystal. Breathing softly, let us consider the extraordinary story of Henrietta Swan Leavitt, a woman whose work transformed cosmology and who received almost none of the recognition she deserved in her own lifetime. In the early 20th century, Leavitt worked as a human computer at the Harvard College Observatory, one of a group of women employed to analyze astronomical photographs. Studying images of the large and small Magellanic Clouds, she noticed something profound. A class of variable stars called Cepheids, which pulsate in brightness over regular periods, showed a clear relationship between the length of their period and their luminosity. The longer the period of pulsation, the intrinsically brighter the star. This period-luminosity relationship, Leavitt's law, meant that Cepheid variable stars could serve as standard candles. By measuring how long a Cepheid takes to pulsate, you can calculate its true brightness, and by comparing that to its apparent brightness as seen from Earth, you can determine its distance. This discovery became the first rung of the cosmic distance ladder that Edwin Hubble would later use to measure the distances to other galaxies and discover the expansion of the universe. The entire modern understanding of cosmic scale, of how large the universe is, of how fast it is expanding, of the evidence for the Big Bang itself, traces back to a pattern noticed in photographic plates by a woman working at a desk in Cambridge, Massachusetts, who was paid 25 cents an hour and who died before the full magnitude of her contribution was recognized. The history of science is full of such stories, and their telling is a form of justice, however long delayed. Let us now turn to one of the most counterintuitive and beautiful revelations of 20th century physics, the concept of wave-particle duality, and what it tells us about the fundamental nature of light and matter. For centuries, the nature of light was debated. Newton believed it was composed of particles. Huygens and later Young demonstrated that it behaved as a wave, producing interference patterns. Einstein in 1905 showed that light also comes in discrete packets of energy, photons, exhibiting particle-like behavior in the photoelectric effect. And then de Broglie extended the paradox further. Not only does light behave as both wave and particle, but matter does too. Electrons, protons, entire atoms, all of them exhibit wave-like behavior under the right conditions. The wavelength of a moving object is inversely proportional to its momentum. For everyday objects, this wavelength is so incomprehensibly small as to be undetectable. But for electrons and atoms, it is measurable, and it governs their behavior in every semiconductor, every laser, every transistor in every computer and smartphone that has ever been built. The wave nature of the electron is not an abstract curiosity. It is the operating principle of modern technology. Every digital device you have ever touched works because electrons behave as waves. The paradox at the heart of quantum mechanics, the refusal of matter to be simply one thing or the other, is not a problem waiting to be resolved. It is the truth about the universe at its most fundamental level. Reality, examined closely enough, declines to be what we expect. As we rest in that gentle strangeness, let us consider one of the most humbling and awe-inspiring aspects of our position in the Milky Way. The fact that we orbit the galaxy at just the right distance from its center to avoid some of the most hostile environments in the cosmos, in what some scientists call the galactic habitable zone. Near the center of the Milky Way, star density is enormous. Supernovae occur far more frequently. The radiation environment is intense. Gravitational perturbations from densely packed stars would disrupt planetary orbits and send comets and asteroids hurtling through inner solar systems at catastrophic rates. Too far from the center, and the interstellar medium becomes metal-poor, depleted of the heavy elements needed to form rocky planets. Our solar system sits at a distance of about 26,000 light-years from the galactic center, far enough to avoid the violence of the inner galaxy, close enough to have inherited sufficient chemical richness from previous generations of stars. This position, sustained across 4.6 billion years of stable orbital motion, has given Earth a relatively calm neighborhood in which to develop life, maintain oceans, and sustain the long biological experiments that eventually produced complexity and consciousness. We did not choose our address in the galaxy, but the address we were given turns out, on examination, to be one of the better ones available. Let us now breathe and turn towards something intimate and immediate, the nature of color, and the remarkable story of what light reveals about the chemistry of the cosmos. When white light passes through a prism, it fans out into the familiar rainbow of the visible spectrum: red, orange, yellow, green, blue, violet. But when light from a star passes through a spectrograph, an instrument that spreads light into its component wavelengths with far greater precision, something extraordinary appears. Thin, dark lines crossing the spectrum at specific, precise wavelengths. These are absorption lines produced when atoms in the star's outer atmosphere absorb photons of specific energies as light passes through on its way toward us. Each element absorbs light at its own characteristic set of wavelengths, leaving its own unique fingerprint in the spectrum. Hydrogen absorbs at one set of wavelengths, helium at another. Sodium, calcium, iron, magnesium, each leaves its own unmistakable signature. By reading these spectral lines, astronomers can determine the chemical composition of a star millions of light-years away without ever leaving Earth. They can measure its temperature, its magnetic field, its rotational speed, and through the Doppler shift of the lines toward red or blue, its velocity toward or away from us. The spectral line that revealed hydrogen in the Sun's atmosphere is the same spectral line that, shifted toward the red, tells us the universe is expanding. The light of a star is not merely illumination. It is a complete biography, written in the language of quantum mechanics, waiting to be read. Drifting onward, let us consider a phenomenon that occurs at the boundary between the living and the cosmic. The extraordinary sensitivity of migratory animals to Earth's magnetic field and what it reveals about the deep entanglement of life with the planet's geophysical systems. Many species of birds, fish, sea turtles, and insects navigate using Earth's magnetic field as a compass and a map. European robins can detect the inclination of magnetic field lines and use it to determine their latitude. Sea turtles imprint on the specific magnetic signature of their birth beach and return to that precise location decades later to lay their own eggs. Some migratory birds appear to use a quantum mechanical process called radical pair mechanism in their eyes, light-sensitive molecules that create pairs of quantum-entangled electrons whose spin states are influenced by the direction of the magnetic field, effectively allowing the bird to see the magnetic field superimposed on its visual world. Life has not merely adapted to the physical environment of Earth. In some cases, it has evolved to directly sense and navigate by the planet's geomagnetic field, a field generated by the churning of liquid iron in Earth's outer core, itself powered in part by the radioactive heat of ancient stellar explosions. The robin orienting itself for migration is, in a roundabout but real sense, navigating by the energy of long-dead stars. And here, as we draw softly toward the close of this passage, let us hold one of the most profound and quietly comforting truths that emerges from the whole of this long journey. The concept of cosmic continuity and what it means to be a temporary form of something permanent. You are not matter that has consciousness. You are the universe, locally and temporarily organized into a form that is conscious of itself. The atoms that make up your body will not cease when you do. They will disperse into air, into water, into soil, into other living things, eventually back into the great cycling of matter that has been flowing through forms since the solar system was young. The energy patterns that constitute your memories and personality are sustained by the physical processes of your brain. When those processes cease, the patterns will dissolve. But the atoms themselves, each one forged in the heart of star, each one older than the Earth, will continue their long journey through form after form, world after world, for billions of years to come. You are a temporary intensification of the universe's capacity for awareness. A brief, bright, particular arrangement of ancient matter that has achieved the extraordinary feat of knowing that it exists. The impermanence of that arrangement does not diminish it. A wave is no less real for being made of water that was ocean before and will be ocean again. You are a wave. The ocean that made you and will receive you again has been here since nearly the beginning, and is not going anywhere. We breathe out all the way, and we let ourselves be held by everything this journey has gathered. The phosphorus in Enceladus's plumes, completing the chemical alphabet of life in a dark ocean beneath alien ice. The symmetry breaking of the early universe, cooling from perfect unity into the rich and structured world we inhabit. Henrietta Leavitt, noticing a pattern in photographs at 25 cents an hour, handing science the key to the scale of the cosmos. The wave-particle duality that powers every digital device ever made, reality refusing at its deepest level to be one thing or the other. Our quiet address in the galactic habitable zone, far enough from violence, rich enough in chemistry, stable enough for life. The spectral fingerprints of elements, writing the biography of every star in the language of light. The robin navigating by quantum entanglement in its eye, guided by the energy of ancient supernovae. And the wave, the wave, temporary and real and made of something that was here before the Earth and will be here long after, carrying in its brief, form the most extraordinary capacity the universe has yet produced. The capacity to know that it is here, to feel the weight of deep time and the warmth of distant starlight, and to find in all of that vastness something that feels unmistakably like home. Rest now. The universe rests with you. We return, and each time we return, something has shifted. Not in the universe, which has been doing what it has always done with extraordinary patience and consistency, but in us. In the way the words settle. In the way the vastness feels less like distance and more like depth. We have been at this long enough now that these passages have become something like old friends, familiar in their rhythms, reliable in their warmth, and still, even after all these journeys, capable of surprising us with something we did not know we needed to hear. The universe is endlessly generous with its wonders. We are endlessly grateful to receive them. We breathe and we begin. Let us open this passage with one of the most quietly magnificent ongoing stories in the history of space exploration, the Mars rovers, and what they have revealed about a world that may once have been not so different from our own. Since the first successful Mars landing in 1976, a succession of spacecraft have revealed a planet of extraordinary geological complexity and haunting beauty. The Curiosity rover, which has been operating in Gale crater since 2012, has driven more than 30 kilometers across a landscape that preserves, layer by layer in its ancient sedimentary rock, a detailed record of Mars's early history. A time when rivers ran across its surface, lakes accumulated in basins, and the chemical conditions necessary for microbial life were present. The Perseverance rover, which landed in Jezero crater in 2021, has been collecting rock cores from what was once a river delta, samples that will eventually be returned to Earth by a future mission for analysis with the full power of terrestrial laboratories. Perseverance has also carried a small helicopter called Ingenuity, which made the first powered, controlled flight on another planet in April 2021, a moment as significant in its own way as the Wright brothers' first flight at Kitty Hawk. Each Mars mission extends our reach a little further, deepens our understanding a little more, and keeps alive the extraordinary possibility that the second planet in our solar system to develop life may have been not Earth, but its smaller, colder neighbor. As we drift from the russet plains of Mars, let us consider one of the most elegant and far-reaching ideas in all of modern cosmology. The concept of the cosmological constant and the strange journey it has taken through the history of physics. In 1917, Albert Einstein added a term to his equations of general relativity, a constant he called lambda, the cosmological constant, to counterbalance the tendency of gravity to cause his theorized static universe to collapse. When Hubble's observations in 1929 revealed that the universe was expanding, not static, Einstein called the cosmological constant his greatest blunder and removed it from his equations. For decades, lambda sat in the dustbin of discarded ideas. Then, in 1998, the discovery that the universe's expansion is accelerating brought it back. Something is pushing space apart, faster and faster, against the pull of gravity. The best mathematical description of this force is remarkably identical to Einstein's abandoned cosmological constant. The value required to match observations is extraordinarily small, so small that explaining why it has that precise value and not zero, and not some vastly larger value, is one of the deepest unsolved problems in all of theoretical physics. Einstein discarded his greatest insight for 20 years because the universe was not doing what he expected. When it finally revealed what it was actually doing, it reached back across the decades and vindicated the discarded term after all. The universe, it seems, is more patient with good ideas than we are. Breathing gently, let us turn to one of the most dramatic and consequential events in the history of life on Earth. The Great Oxidation Event, and the extraordinary irony that what was for most life at the time a catastrophic pollution crisis became the foundation for all complex life that followed. Approximately 2.4 billion years ago, a group of microorganisms called cyanobacteria had been performing oxygenic photosynthesis for perhaps hundreds of millions of years, splitting water molecules using sunlight and releasing oxygen as a byproduct. For most of Earth's early history, this oxygen was absorbed by dissolved iron in the oceans, which oxidized and sank as rust, forming the vast banded iron formations we mine today. But eventually the capacity of the oceans and atmosphere to absorb free oxygen was overwhelmed. Oxygen levels in the atmosphere began to rise. For the anaerobic microbes that dominated the early Earth, organisms for which oxygen was a toxic poison, this was a mass extinction event of the highest order. The Great Oxidation Event killed the vast majority of life on Earth at the time. And yet, from that catastrophe, something magnificent emerged. The availability of atmospheric oxygen enabled a new form of metabolism, aerobic respiration, that extracts far more energy from food than anaerobic alternatives. The mitochondria in every one of your cells, powering every thought and movement you make, are the distant descendants of bacteria that learn to harness oxygen for energy. The air you breathe, which sustains your life, was 2.5 billion years ago the greatest environmental catastrophe the living world had ever seen. Let us now consider one of the most recent and breathtaking results from the James Webb Space Telescope. Its observation of galaxies in the very early universe that have challenged some of our assumptions about how quickly structure can form after the Big Bang. Within its first year of scientific operations, Webb detected galaxies existing less than 400 million years after the Big Bang that are far more massive, far more luminous, and far more structurally developed than the prevailing models of galaxy formation predicted they could be at that age. The universe, it seems, assembled its first large galaxies faster than we thought possible. These early galaxies are compact, intensely star-forming, ablaze with the light of young blue stars in a way that modern galaxies, including our own, no longer are. They represent a kind of cosmic adolescence, fierce, productive, and brief before the star formation slows and the galaxies settle into the more measured rhythms of middle age. Webb is also detecting the earliest known supermassive black holes, immense concentrations of mass at the centers of these young galaxies, raising profound questions about how black holes 1 billion times the mass of the Sun could have grown so large so quickly after the universe began. Each new Webb image is not merely beautiful. It is a direct challenge to our best theories, an invitation to revise what we thought we knew, a reminder that the universe is always richer and stranger than our current understanding of it. As we breathe and float gently onward, let us consider the concept of geological deep time through one of its most striking illustrations. The story of zircon crystals, and how a mineral no larger than a grain of sand preserves the oldest material ever found on Earth. Zircon is a remarkably durable mineral that forms in igneous rocks and incorporates uranium into its crystal structure as it solidifies. Because uranium decays to lead at a precisely known rate, the ratio of uranium to lead within a zircon crystal functions as a precise radiometric clock, readable billions of years after the crystal formed. The oldest zircon crystals ever found, discovered in the Jack Hills of Western Australia, have been dated to approximately 4.4 billion years old. Earth itself is only about 4.5 billion years old. These crystals formed when our planet was barely 100 million years into its existence, before the heavy bombardment that reshaped the inner solar system, before any life existed anywhere on Earth, before the oceans had fully formed. And yet here they are, preserved intact in younger host rocks, their crystal lattices still carrying the radiometric record of their birth. When a geologist holds a Jack Hill's zircon crystal, they are holding something that formed when the solar system was still being assembled, that survived 4.5 billion years of geological upheaval, plate tectonics, erosion, and redeposition. A tiny, almost indestructible witness to the very beginning of our world. Let us now turn to one of the most quietly stunning demonstrations of the universe's underlying mathematical order. The strange effectiveness of mathematics in describing physical reality, a puzzle so deep that the physicist Eugene Wigner wrote a famous essay about it in 1960, calling it the unreasonable effectiveness of mathematics. The equations of general relativity, developed by Einstein between 1905 and 1915, predicted the existence of black holes, gravitational waves, and the expansion of the universe, all before any of these phenomena had been observed. The Dirac equation, developed to describe the quantum behavior of electrons, predicted the existence of antimatter before antimatter had been detected. The mathematics of quantum field theory predicts the magnetic moment of the electron to an accuracy of 1 part in a trillion, the most precisely verified prediction in the history of science. Mathematics, developed by human minds reasoning about abstract relationships and patterns, turns out to describe the physical universe with a precision and predictiveness that seems almost impossible to explain as coincidence. Why should the universe be mathematical? Why should abstract structures invented to solve logical puzzles map onto the behavior of matter and energy at every scale we have examined? This question has no agreed-upon answer. It sits at the frontier between physics and philosophy, a reminder that beneath all our knowledge there lies a mystery we have not yet even properly formulated, the mystery of why the universe is comprehensible at all. Breathing slowly, let us consider the extraordinary phenomenon of stellar winds from dying stars, and how the material shed by aging stars becomes the raw material for everything that follows. As a star like our Sun approaches the end of its life, it expands into a red giant, and its outer layers are progressively shed into space in slow but sustained stellar wind. Over hundreds of thousands of years, this gentle exhalation of mass builds up a vast envelope of gas and dust surrounding the dying star, a structure that will eventually be illuminated by the exposed stellar core into the glowing beauty of a planetary nebula. The material shed in this way, enriched with carbon, nitrogen, oxygen, and heavy elements synthesized in the stellar interior over billions of years, becomes part of the interstellar medium. It cools, mixes with hydrogen and helium already present in space, and over millions of years, the turbulence of galactic dynamics and the shock waves of nearby supernovae compress these enriched clouds into new star-forming regions. The material that our Sun is currently burning in its core will one day be returned to the galaxy in its stellar wind and its eventual planetary nebula, available to become part of a new star, a new planetary system, perhaps a new world on which some form of chemistry stirs toward complexity. Every star is both an inheritor and a contributor, consuming the legacy of previous stellar generations and preparing the inheritance for those yet to come. And here in our final reflection for this passage, let us sit with one of the most personally resonant truths that emerges from a whole sweep of cosmic history, the extraordinary improbability of your specific existence, and why that improbability is not cause for anxiety, but for a kind of quiet, astonished gratitude. The universe has been running for 13.8 billion years. In that time, The precise sequence of events that led to your existence has included the formation of a particular galaxy, a particular star, a particular planet in a particular orbit, the emergence of life from chemistry at a particular moment in Earth's early history, the survival of that life through 5 mass extinctions, the divergence of hundreds of millions of species, the particular meeting of 2 individuals among the billions who have ever lived, the particular moment of conception that produced you, and not one of the countless other possible people who might have been born instead. The probability of your specific existence, calculated against all the branching paths that led here, is so vanishingly small that it cannot be meaningfully expressed as a number. And yet here you are, not a version of you, not someone like you. You, this particular arrangement of thoughts and memories and sensations and questions, reading or listening or resting in this particular moment. The universe did not have to produce you. The long chain of accidents and choices and collisions and survivals that led to this moment was under no obligation to arrive here. And yet it did. You are, in the most literal sense, a miracle of specificity, a particular form the universe chose from among all possible forms to take. We breathe out, slowly, completely, and we let the universe hold us for this moment. The ancient delta of a Martian river, its sediments preserving the record of a world that was once wet and alive with chemical possibility. The cosmological constant, Einstein's greatest blunder, and then his posthumous vindication, still pushing space apart at this very moment. The great oxidation event, a catastrophe that became the foundation of everything that breathes. The fierce young galaxies blazing in Webb's earliest images, assembling themselves faster than we thought possible. The 4,400,000,000-year-old zircon crystal, holding the memory of Earth's first century. The unreasonable effectiveness of mathematics, describing a universe that seems almost designed to be understood. The dying stars exhaling their enriched material back into the galaxy, preparing the inheritance for stars and worlds not yet born. And you, improbable beyond calculation, specific beyond measure, here against all odds, in this moment that the entire history of the universe conspired, without plan or intention, but with breathtaking precision, to produce. You are not here by accident. You are here because everything that has ever happened led here. That is not the same thing. Rest in that. The journey continues. It always continues. And you are, and have always been, exactly where you need to be. Thank you for watching. I look forward to making more content for you.